All right, it looks like we're live. Hello, everyone. I'm Chris Rakakis, and I'm joined here today with Yingbo Ma. And what we're going to do today is we're going to talk about Modeling Toolkit. So we're going to dive right into this. I'll be taking a few of these spots, and then Yingbo will join right in, and he'll be doing a bunch of coding along. So what I'm going to be doing, I'm going to start with something that's very high level and really explain a lot of what's going on with Modeling Toolkit. If you don't understand it all, don't worry, because we'll go right back into it and we'll be live coding and showing how all this is done. So let me get that all set up now. And let me start my screen share. All right. Let's see. Yeah. So remember that if you have any questions, please ask your questions at the Pigeonhole. That's pigeonhole.at/MTKJL. Right. You'll be asking all your questions there, and then whenever we have one of these breaks, we'll go back through it. So, once again, hello, I'm Chris Rakakis. I am a applied mathematics instructor at MIT. And I'm joined here with Yingbo Ma, who's a research engineer with Julia Computing. And what we're going to be talking about today is simulating big models in Julia with ModelingToolkit.jl, right? So Modeling Toolkit is a fairly comprehensive library. I did not say differential equations because there's much more than differential equations going on here. But since everything in the world is a differential equation, there will be lots of differential equations that we're showing. So let me start by saying that if you want to show your support, please star our libraries. I cannot stress this enough that basically we need to be able to show to lots of different people that lots of people care about these libraries and lots of people are using these libraries. And so one of the very public ways of being able to just show support that is free is just to click that star button on GitHub. Let me just kind of show you where this is, right? So if you go to GitHub, you go to one of these repositories, you go up here, you click the star, and it makes us all happy, and it makes it so that way we can show everyone how many people care about Modeling Toolkit, Symbolics.jl, differential-equations.jl, Catalyst.jl. We're going to be going through the whole gambit of JLs today. So special thanks to people who have very contributed and really have funded a lot of these efforts. So Simon Frost with the Microsoft Pandemic Research Preparedness gave some funds to the MIT Julia Lab for really kicking off this project in a nice way. So thank you very much. It was a lot of funding from the RPE program, so thank you, David, to you, and that was run through Julia Computing, and I'll mention that Modeling Toolkit is a part of Pumas AI, and so there's just so many different ways that this is now being put to use in the real world, and I have to thank everyone who really got this off the ground and running. Especially all those who contributed it in various different ways. So, we've gotten a lot of help from Chris Loftman at Mitsubishi Electronic Research Lab, but also a lot of individuals like David Sanders and Samuel Isaacson. They seem behind the scenes according to this project, right? You might not see them all the time, but as the Modeling Toolkit people, but they really contributed a lot of the ideas that made this what it is today. So, share your support and thank everyone who's involved with this project. Now, there's going to be a lot of JuliaCon talks on scientific machine learning. I'll post this in the channel during one of our breaks, just so that way you know. These are other talks that if you're interested in this general topic of making differential equation modeling fast, doing modeling and simulation, doing adding in machine learning with it, there's just so many talks happening at this JuliaCon. Many of these featuring differential-equations.jl and ModelingToolkit.jl, and so just check all of them out. I mean, this is just one talk out of many that is focusing on this topic. So you're going to have a great week next week. I can guarantee that, even without seeing them. So what's a nice outline of what we're going to be talking about today? So first, we're going to start with an overview of scientific machine learning and Modeling Toolkit, right? So I'm going to be giving a talk, almost like a seminar talky kind of thing to start, just so that way you have a feel for what Modeling Toolkit actually does. I think everyone has a different idea on what it does, and you're all correct. And so it'll take a little bit of time to really explain the whole world of modeling that we're focusing on. Then we'll get right into an introduction to Symbolics.jl, because Modeling Toolkit's core is this new computer algebra system, right? Kind of think like SymPy, and since it's pretty brand new, we wanted to make sure that we introduced everyone to what's going on with our symbolic ecosystem and how do you use all these symbolic tools. After we do some symbolic modeling, we'll go to the ODE modeling with Modeling Toolkit, right? So this is symbolic ODEs with Modeling Toolkit. How do you mix, how do you do automatic parallelism, acausal modeling, and all these kinds of deals? Even define what acausal modeling is, right? We'll go through all of that. And then last, depending on how much time we have, we'll go to beyond ODEs, right? So Modeling Toolkit will do stochastic differential equations, nonlinear systems, optimization. You can even solve PDEs with neural networks, right? And so we're after with whatever time we have at the end, go through all these nice little points about how this idea of this symbolic modeling ecosystem extends to this entire world. So, okay, what is Modeling Toolkit? One way to define it is that it's the symbolic side of the SciML organization, right? So, we have all these numerical tools like diffie-q flux and the differential equation solvers, and Modeling Toolkit is the symbolic part of that. You define your equation symbolically, and then it automatically handles it and turns it into things that are solvable, etc. Right? So that's one way to think about Modeling Toolkit. Another way to think about it is it's a symbolic numeric optimizer, right? It takes your model and it does some things on it, and it says like, oh, if you change your model here, then now it's more parallel. If you change your model here, now it's more stable to solve. If you change your model here, now it's faster to solve. So it's like an optimizer on your model. Another way that you can think about it is that it's a causal modeling system. So things like Modelica, Simscape, Simulink, all these kinds of things that are based around doing engineering modeling systems, where you define different parts of your model and you connect them all together, and then you solve the big model, right? That is one other way to think about Modeling Toolkit, and you'll see that is a subset of what this world entails, right? And the last but not least, Modeling Toolkit is a DSL building tool. So these domain-specific libraries for neuroscience, for chemical reactions, for power systems, all these different when you have a scientific domain, you might think about Modeling Toolkit as something where you say, I'm going to take my domain, I'm going to make it so that way the user writes science and it turns into math, and then Modeling Toolkit takes math and turns it into code, right? And so what is Modeling Toolkit? Which of these is it really? All of them are correct, right? In some sense, it is all of these at the same time, which might sound at first like it's some weird, crazy thing. But once you see how Modeling Toolkit works, you'll see that it actually all flows nicely together. All of these are actually the same exact problem, right? Because what we want to do with Modeling Toolkit is we want to represent models symbolically, so that way we can computationally change them before we solve them, right? So we can computationally make our tools better at handling the math that you give us. And so, well, if we also have the model symbolically, then we're the ones generating code. So we can just make sure we generate bigger, better, faster code than before. And, well, if you give us the model symbolically, then we can compose models together, right? If we know the mathematical structure, we can start to do simplify, we can replace things, we can substitute equations. And so acausal modeling actually just falls out of this idea. And then, Modeling Toolkit is a DSL building tool because, well, if it does all these things, if it does all this fast code gen, then why would you write something that writes code yourself, right? Why wouldn't you just let Modeling Toolkit make it parallel, fast, sparse for you? And so, in some sense, it's all of these things at the same time because of the symbolic ecosystem that it puts together. So this is what, this first part where I'm introducing Modeling Toolkit, I want to just kind of show you how this world all kind of meshes together, and how all these tools combine to give you this kind of a system. I'll put a quick disclaimer on here, right? So I had to find some Creative Commons licensed caution tape for this. Basically, Modeling Toolkit is not close to complete, and there are some big changes planned. What we show in the workshop will be the stable portion. So a lot of things like the differential equation modeling, the acausal modeling systems, these are all pretty clearly cut and dry, and those are the things that we know work, right? But there are some other aspects to Modeling Toolkit which are not quite complete yet, but are kind of on the periphery that we could show. But we'll be waiting until probably the next workshop on this. So things, control theory and optimal control. A lot of people are interested in this. We'll not be touching on exactly how you do control theory today, but that'll be a great topic to follow up with. How do you generate C code for embedded devices? How do you build an ML framework within Modeling Toolkit? I mean, I can give you the short thing on how you could just build Jackson Modeling Toolkit and as like a 1-month project, but see reverse propagation.jl. This talk will not be about how do you do that. How do you generate cluster and GPU code? Other topic. How do the algorithms work? When I say, oh, magic structural simplify is the god of all simplification algorithms, we won't explain exactly how that works because that's a 3-hour topic itself. How do you do automated model discovery and such? Well, we won't be touching on some of those topics, right? So we will be focusing on just a very, very small part of Modeling Toolkit, but it will already be very, very large, and so we will stop there, right? But just so you know, you can find a lot of these other details in the documentation throughout the Scientific Machine Learning Library, and there's a whole host of other JuliaCon talks which are about these topics. So now let's start on the big overview of the SciML libraries and Modeling Toolkit. Let me start with the first question that everyone has to ask, which is, who's using it and why should I be excited, right? There's this weird thing that Chris is saying everyone should use, but why should you, as a potential modeler, think that this is something that could improve your modeling workflows, right? Well, the thing is, we already have results, right? So it's kind of been like this silent project in the back where everyone knows about differential equations.jl, but really, Modeling Toolkit has been one of our prime projects in the last 1.5 years, and we have some very amazing results already, such as, Jonathan Dingelman, he gave a talk at SciMCSC 2021. You can find this talk on YouTube, where he went and showed that, translating his models for NASA launch services from Simulink to Modeling Toolkit gave a 15,000 times acceleration. So that's a small difference, right? But it does help if you're trying to do this. Now, another case where this showed up, and actually one of the things that really founded Modeling Toolkit, was that Yingbo and I were working on a project with Pfizer where we showed that we can take their model and actually automatically translate it to GPU code, where Modeling Toolkit was actually a substantial part of that because it was generating the Jacobian functions for doing the SPIMD GPU computing. Right, so we won't mention too much about the GPUs here today, but just know that this Modeling Toolkit framework, it can generate all this kind of cool code for doing all this work, parallel and fast, right? It's also one of the pieces that's behind Pumas, which is this pharmaceutical modeling and simulation software made by Pumas AI, right? That's all built on top of Modeling Toolkit. And so a lot of the successes of Pumas itself, you can then relate back to saying, yes, that's a success of Modeling Toolkit, such as if you look at, the Pumas AI website, you'll see that there has been a very nice, showcase about how, Pumas and thus, these modeling tools has emerged as the go-to tool of places like Moderna Therapeutics in 2020 as a way to be able to accelerate, all the modeling or all the clinical trials that were going on during that year. Right, so there's already been a lot of groups who have been, picking up these tools and been using it under the hood, even though it's kind of been like the silent killer, And so there's a lot of ways that people have already built an ecosystem around Modeling Toolkit for you. So, if you have models in something like SBML, CellML, BioNetGen, these kind of biological formats, what you'll see is that all these readers are actually they're giving you Modeling Toolkit models in the end, right? So if you have these kind of file formats that describe models, a lot of these prep packages in Julia are now giving you Modeling Toolkit models as the form to then go and solve and generate solutions with, right? So knowing Modeling Toolkit then is probably a good thing to know. And we've actually been able to show that some of the clever things within Modeling Toolkit can actually take those original simulations and further simplify the code that is generated from them to even give you more acceleration. We'll mention too much about how that's done. We'll just kind of say there's magic simplification algorithms, and thank Yingbo, thanks Shashi for those. So not even just Modeling Toolkit, but also the symbolic simplification libraries. The Symbolics.jl has been finding a lot of use. So there's this one post in the Slack channel where basically someone was trying to use SymPy. It was running a computation for 20 minutes. he decided that within the 20 minutes, he might as well just give Symbolics.jl a try because it was just released and it ran in 1.5 milliseconds, right? So that was a nice 2,370 times speed up for his real world application in a robotic system. I mean, we don't know if, it's hard to tell if 2,000 times speed up will change your, change your workflows, but for some people it definitely does, right? Now, Modeling Toolkit, there'll be a talk about JuliaSim at part of JuliaCon, but JuliaSim is this thing that's being developed by Julia Computing, where it can take your Modeling Toolkit models and automatically transform them into these machine learning hybrids. And so what this can do then is it can accelerate your models by an extra 10x to 100x. And so what we actually demonstrated here was we can be, models that are written in Modeling Toolkit can be about 6 times faster than Daimola. But then when you do this machine learning integration that we have with Modeling Toolkit, you can actually get up to about a 60 times to 570 times acceleration over these Modelica-based modeling tools. So this was for a air conditioning model. And so, this kind of shows that there's a whole range of different engineering domains that have really started to pick up this tool. The Modeling Toolkit was kind of in the background when it was mentioned last year at JuliaCon 2020. So we showed it last year how we can do really nice things like embed neural networks with indifferential equations to be able to use prior knowledge with equation discovery and then generate symbolic models. It turns out that those symbolic models that we generate are Modeling Toolkit models, right? So, the Modeling Toolkit is this world that we were able to send, data turns into model. How do you represent that in Julia so that way it's useful? You represent it with Modeling Toolkit. There'll be a nice talk this year that actually extends that whole world, and it basically shows how you can use prior knowledge along with neural networks to be able to give the probability that certain terms are missing from your model, and it'll actually give you you have a 80% chance that you're missing a quadratic term in your model, and that representation of what the missing model is a Modeling Toolkit representation. So if you're not seeing it by now, basically the idea is Modeling Toolkit is showing up everywhere in the Julia ecosystem. So let's so since a lot of people are using it, right, let's go one step a little bit lower. And what is the big picture with Modeling Toolkit and symbolic numerical programming in Julia? Like, what does the code look like? What are you actually doing? What kinds of problems does it solve, right? So Modeling Toolkit, you can think about it as like a modeling front end to a symbolic ecosystem, right? So you can you define these symbolic variables, and then you say my symbolic representation of an ordinary differential equation is this. Here's the differential with respect to t. So here's the second derivative of x with respect to t. It's equal to here. The first derivative of y with respect to t equals here. You just write down your equations in the symbolic form. And now the key to Modeling Toolkit, though, is that after you define your ODE system, it has all these ways of transforming your equations, right? So you know that an ODE solver wants this to be in first order form. Well, why not just tell Modeling Toolkit to take this second order ODE and transform it into a first order ODE for you, right? And then after you transform it, then you're able to make something that's solvable and solve. And so what it's really doing under the hood, right, is it says, well, one way to be able to solve a second order ODE is to define a variable that is the first derivative, and then the derivative of the first derivative is your second derivative, right? And so it will do this transformation to build you a new system, and this is the system that you actually solve. And so this is like the key idea behind Modeling Toolkit. It's that you can write models in a very flexible mathematical form, and then you can let Modeling Toolkit transform your models into ways that are better to solve, faster to solve, etc. So you build your model at a high level, and then you let it run a bunch of transformations, and then you do a code generation down to a numerical problem. Right now you're back to differential-equations.jl. Now you have an ODE problem, and you hit solve on your ODE problem, and boom, now you have the solution to the ODE, right? So really, when I say though, build a model. Building a model in Modeling Toolkit doesn't have to look like this. It'll look very different depending on a lot of cases. So here, for example, is a mixed continuous and discrete differential algebraic equation, right? You can start to say, well, I have differential variables and I have difference equations. So at every dt equals 0.1, do it a discrete update. but also be running a differential equation. So, here's like log Volterra plus some extra things on it, plus a algebraic term, which is only defined implicitly. And so you can kind of throw all these ideas together and just say, this is the math, handle it for me, and it'll generate the right code for differential-equations.jl to then be able to simulate it. You can do things like observed variables, so variables that you don't want to be solved, but you want to plot the solution of. You can do variables like control variables and add in continuous callbacks and event handling and all that. So it's this, this, when you say ODE system, what I really mean is this really flexible, like anything that is kind of ODE-like plus kind of idea. But the cool thing about Modeling Toolkit is that if you don't feel like using Modeling Toolkit, you don't have to use Modeling Toolkit to use Modeling Toolkit. So here's an example where we say, oh, here's an ODE problem represented by differential-equations.jl. But what we can do is we can say, well, you might want to use this symbolic modeling system because whoever wrote this code doesn't know anything about code optimization. So we can use this thing called Modeling Toolkit ties that actually takes the code written for differential-equations.jl. It turns it into a Modeling Toolkit model, and then you can start to run transformations like, oh, let's optimize this code, let's build an analytical Jacobian, and now let's solve it. And it turns out this gives you about a 10 times acceleration on this kind of code without any effort. And so if you don't understand why that optimizes code, then you are the perfect member of the audience to use Modeling Toolkit, because it will give you some really nice accelerations, and you just kind of say thank you, right? But yeah, so that's the key. You don't even have to use the symbolic modeling language, and it's still going to be affecting your code. It's still going to be optimizing your code, and that's why it's actually being used all throughout the SciML ecosystem at this point. And models can come from all sorts of these domain-specific libraries, right? So here, for example, is Catalyst.jl, where you define a chemical reaction network. And then you see that there's this one step in its documentation that says convert to an ODE system from this repressilator chemical reaction, right? So you define some kind of chemical reaction network, and it still goes into Modeling Toolkit. And so everything that we talk about here about what do you do when you have this ODE system? What kinds of transformations can you do? What kinds of parallelism that you could do? Well, Catalyst.jl has all of those features for free because it just defines how to represent this guy as an ODE system. And so, there's many different ways to kind of get ODE systems out in the end. You kind of have this funnel going on now where Pumas is giving you ODE systems. Catalyst is. Orbital Trajectories.jl has another talk at JuliaCon and another talk on YouTube. Go watch Dan Padilla's work. Power Systems Dynamics, a lot of Jose Daniel Lara's work now can funnel into Modeling Toolkit. Conductor.jl for neuroscience modeling, brand new. It's like Neuron or Brian, but now it's using Modeling Toolkit to get off its speed, parallelism, and all that, right? So you have all this huge ecosystem that's now funneling into, everything is giving you an abstract ODE system, and then so you might want to learn Modeling Toolkit because it's starting to be this kind of central idea of how to represent a differential equation or how to represent a mathematical model in the Julia ecosystem. And so, another talk to kind of feature on this is that, there are a lot of these file format readers, as I mentioned, SBML, CellML, and BioNetGen, they also feed into the same form. And so there would be a nice talk about all these other ways to be able to get models, from systems biology domains and these other domains at this same JuliaCon. So once you have a model inside of Modeling Toolkit, what can you do with it, right? You can do a bunch of transformations. And what can you do with that? Well, you can analytically calculate things like Jacobians or Hessians. You can analytically determine sparsity patterns, right? I mean, we know all of your equations, so we can differentiate them, and we can analytically build whatever we want based off the derivatives, right? But since we're also generating your code, we can parallelize your code for you, right? We're building the code for differential-equations.jl, and we know how it works. We built differential-equations.jl, so we can make sure that we generate the most optimized code for it. But there's also nice other things that it will do as part of this, right? So here, for example, I define a differential equation by saying, the derivative of x with respect to time equals the right-hand side, and the right-hand side equals these equations. And so it's two equations, but if you run this thing called structural simplify, it actually realizes that there's only one equation that you need to run, right? And so it'll solve just one equation, even though you wrote down two. But then you can still plot the solution of both equations because it remembers how to calculate the right hand side value, even though it deletes that extra equation from the way it's solving. Right. So structural simplify. I'm going to mention it again and again. Structural simplify is the god of transformations. It is the way of thinking about what does simplify of a model mean in its most general form. So let's actually dig into a few cases of that, though. So let's say you wanted to build a model with a system of subsystems, right? So we'll be going into exactly how do you do an RC circuit like this as one of our coding examples. For now, what I'm going to say is, we can pull in JuliaSim, which has a whole pre-built model library for Modeling Toolkit, and then you can say, well, I have an RC circuit, so let me grab a resistor capacitor. You can then define equations for how these things all relate. And so you can have an ODE system of ODE systems where you're then just saying how different pieces of ODEs are combining, right? And then you might get out 16 equations, but structural simplify, say, I found a way to be able to solve these 16 equations by only solving 2 of them. But if you ask for the solution of any of the other variables, I'll give you them when you want them. Right. So this really kind of gives you a way to be able to write down the model in the most expressive form without having to give up any of the speed, because it's just going to change the model for you. It's going to fix your code. And so you might as well let it. And so what are some other transformations that you get from this? Well, let's look at a pendulum, right? Pendulums are hard. That's a very funny statement, right? Because you know how to write down a pendulum in a way that works. You use Euler angles. But if you write down a pendulum like this, you'll actually find that it's not solvable by differential-equations.jl. It's not solvable by sundials. It's not solvable by ODE solvers. And the trick is that you should take your equation, you should differentiate this last one 2 times, and then you should substitute in these other equations and get this one. And if you do that, then your pendulum is now very easy to solve. So this is something called DAE index reduction. And if you have no idea why that trick would work, then that means you are the perfect person to be using Modeling Toolkit because it'll do it for you, right? And so what does that look like? Well, remember that Modeling Toolkit models can come from code, right? So here's a differential-equations.jl code. You define the pendulum in this Cartesian form. You try to solve it, and it says, oh, I can't solve the model. It's unstable, right? It turns out that the reason why this is unstable is because it is a index 3 DAE, et cetera, details. This is not how you write a pendulum well that solves well, right? So instead what we do is you say, Modeling Toolkit ties my model, transform into symbolic. Now let structural simplify fix my model. Build an ODA problem of the fixed model, right? So regenerate the code that is better. Now solve it here, and now you get a good pendulum, right? So Modeling Toolkit is then you can kind of think about it as this intermediate that fixes your code for you. And once again, if you don't know why that would fix your code, then you're definitely perfectly suited to be the audience of Modeling Toolkit. Now, what kind of transformations do you get from Modeling Toolkit? Well, you also get ones like machine learning acceleration. So I'll be giving a talk later at JuliaCon about how JuliaSim allows for machine learning, accelerated modeling, and simulation. You can think about model order reduction as another transformation in your model. It's just an approximate transformation, right? So we can take this really big model of, say, an HVAC model, and then we say, well, generate the ODE system of the surrogate, and now it can say, well, here was your original 8,000 equation model. You can get to a 5% error by instead solving this 100 equation model. And it just knows how to automatically generate the smaller set of equations, so that way you can get this 60 times 800, 600 times acceleration from your model. That's just another transformation, right? These are just other ways of taking symbolic models and generating new symbolic models before you have to run them. And now here's a really nice one because it actually comes from someone in the ecosystem. So here I'm taking the chemical reaction network again, the repressolator. And this is actually, in its original form, chemical reactions are a stochastic model, right? They give you these random outputs. And there's a way to be able to find that. And now some very smart people said that, well, if instead of trying to do a full stochastic simulation, you could, do this to write out all the ODEs for what the mean, what the variance, and all this is. But no one would ever want to do that by hand, right? So what you can do instead is you can say, well, here's my symbolic model, generate what the mean equations are and the moment equations are, and make this into an ODE system. And here's the ODE system that you can then solve, and it'll give you your means and your variance of the stochastic model, right? So all these different things where it's like, oh, hey, the best way to actually do this is to do this transformation before you do the solve. Well, all of those techniques that are not numerically possible are now possible through this symbolic system, right? You can do all these transformations for you. Don't do them by hand. Now, Modeling Toolkit does extend far beyond ODE systems, though. So here, for example, is an example of a nonlinear system, right? We can, we say that, oh, we want to find the simultaneous solution of x, y, and z has all of these equations equal to 0. Well, you can say that this is a nonlinear system. The syntax looks exactly the same as the ODEs, but now you call a nonlinear solver, and boom, it is going to be the thing that solves this nonlinear system. Now, what does structural simplify do here? Well, as I mentioned, it's like some god of transformations. It's like what simplify means in its most pure, Greek sculpture form, right? And so let's say you have this as your nonlinear system, right? U1 equal sine of U5, all these things together, right? If you're to put this into try to do this with something like NL solve, if you want to solve simultaneously for U1 or U5, you might find out that this is something that can be, it takes longer to solve than you'd expect. And the reason is because Newton methods have a cost of O of n cubed. But what structural simplify will do here is say, well, you don't actually have 5 unknown equations because U1 equals this, U2 equals this, U3 equals, well, if I've already solved for these ones, you plug this in here, etc., right? So it finds this way of being able to what's known as tear your nonlinear system. So that way you only have one equation to solve for, right? This is exactly the, mathematically, that's exactly the same as the one that you wrote down, but you probably never want to actually do that by hand. But now Modeling Toolkit will say, well, yeah, define your nonlinear system and now simplify it. Now you only have one equation. From this one equation, it knows how to recreate all the others. And so now your computational cost dropped from 5 cubed to 1 cubed, right? Which is a full 125 times difference in the amount of computations you have to do, just because it did all these transformations for you ahead of time. Right, so that's pretty nifty, and this is the reason why we more and more have been telling everyone, like, don't write your code by hand. Let Modeling Toolkit do it for you, because every once in a while you'll find these, most of the time you'll only get about 100 times kind of cut off, but a lot of times you'll get a lot more going on because of all these nice little symbolic things going on. And so Modeling Toolkit kind of matches the SciML organization by being its full full symbolic counterpart, right? There's linear solvers and there's ways to do linear equations in Modeling Toolkit. There's nonlinear solvers, and well, I just showed you nonlinear system. There's differential equations and there's symbolic differential equations. There's galactic optim for nonlinear optimization. Well, and there's a symbolic optimization problem, which you can kind of think about as like a generalized idea of jump. There's quadrature problems, and there's these, and there's also a way to be able to do all these partial differential equations inside of Modeling Toolkit. And this is really where I'm going to end by showing this, because partial differential equations in general cannot be done without thinking about them symbolically, right? Because every partial differential equation is in some sense a different kind of equation, a different form. But what we've done through this whole system is we've given a way to be able to say, here's the partial differential equation, and have a whole suite of tools, then do all the transformations needed to be able to make all partial differential equation modeling automatic.
Great.
Yeah.
Sorry to interrupt. The chat is saying that you have some audio glitches.
Oh no.
Yeah, Chris, really quick. Your audio is glitching like every fifth or sixth word. There's like a weird, I don't know how to describe it. Do you want to switch? Do you have another audio device you can switch?
Yeah, is it better now?
Let's see. You want to keep talking and I'll tell you?
Yeah, is it better now?
It sounds okay.
Okay. Yeah. Well, I switched. Yeah, it looked like I had it on the wrong one. Sorry about that. But yeah. So let's get to the what is a partial differential equation? Well, you might want to think about a partial differential equation in this mathematical form, right? This is, so here, for example, is a Poisson equation, second derivative of u with respect to x plus the second derivative of u with respect to y equals this expression. You can just write this out symbolically, right? This is the second derivative of u with respect to x plus the second derivative of u with respect to y equals this thing symbolically. You define your boundary conditions, and you define the domain that you want to solve on, and this is a symbolic PDE system, right? And now let's say you want to do method of lines, right? So I gave a whole talk at JuliaCon 2018, which is like, well, the way to solve this PDE is to do, et cetera, et cetera. You do a bunch of transformations. What Modeling Toolkit does is transformations, right? So what you can do is you can say, well, here's a symbolic PDE system. Let's just automatically transform it into things that are its solution. So here, for example, as you say, well, let's do a method of lines finite difference. This will spit out an ODE problem, where when you solve the ODE problem, or it gives you the differential equation solution. Actually, this one doesn't have time, and so this one will actually spit out a nonlinear system, where when you solve the nonlinear system, it gives you out the PDE solution, right? So there are other ways to solve PDEs as well, right? So you can say, well, here's this way of describing the PDE. And with exactly the same PDE description, you can define a neural network and then use a physics-informed neural network. And now the neural network is the solution to the PDE. And it's literally the same exact PDE definition, but now you're using entirely different ways of solving it. And there's a nice JuliaCon video that's going to show up this year about using physics-informed neural networks to solve these kinds of PDEs, right? And so there's many different ways to be able to solve PDEs. And what we're doing is we're building a whole symbolic modeling ecosystem to on top of we're building a whole ecosystem of discretizers, so that way finite volume, spectral, finite element methods, all of them can be used on the same PDE description. So that way you as a modeler just have to think, here's the math, do everything else for me, right? And you really need a symbolic way of representing models to be able to do that in this general form. And so where we get to with Modeling Toolkit is it's like it basically is this tool where PDEs turn into PDE system, Acausal models go to ODE system, but PDEs also transform into ODE systems, and surrogate models turn into optimization systems. So you have this whole web about how systems are turning into systems, but then they turn into optimization problems and ODE problems, which then use all of these other Julia packages under the hood to do the numerical solving. And so there's this huge stack that you actually get to use, but when you don't really need to worry about using it too much, right? You just kind of say, this is my mathematical model, turn it into a problem and solve it, and actually will automatically choose the solver and everything for you, so you don't need to worry too much about all the details. But all the other talks from all the other years kind of go into how you can make all the little choices and that are then involved in this process. And so what is Modeling Toolkit? It depends on who you ask, but at the same time, it also is all of these pieces all at the same time, right? So it is the symbolic side of Modeling Toolkit. It is a symbolic numeric optimizer. It is an Acausal modeling system, and it is a system that people are building DSL tools on top of, right? It's all of these ideas at the same time. And so now what I want to get into is the introduction to Symbolics.jl, right? Basically, let's start to walk through how do you use this symbolic ecosystem and how do you do symbolic modeling in Julia, so that way we build up from the ground up, right? How do you define equations? Let's define equations before we get to defining ordinary differential equations. So let's dig in a little bit. So when you have this idea of a symbolic model, you're going to be writing it in Modeling Toolkit, but it's built on all these pieces that actually come from Symbolics.jl, right? It's like SymPy. It's this computer algebra system where you define like, oh, here's my parameters, here's my variables. These equations are all Symbolics.jl, but then you put these pieces of symbolics together into an ODE, and then you let Modeling Toolkit transform this into code for differential equation modeling, where you then are back in differential equations land, right? So it's this whole kind of connection between these tools that are going on here. Symbolics is a type-based computer algebra system, and so by default, everything is just real numbers. But you can say, well, I want a symbolic array, and this is actually, not an array of symbols; it's a symbolic array. And I want a complex valued symbolic variable, and and all these things then have different simplification rules and different algebras that they're associated with. not going to go too much into different rewrite systems, but the way that all of the rule handling and simplification is actually all written in Julia itself. These pieces, symbolic utils and metatheory.jl, and so you can always extend the simplification rules as you want, and all this is built as a pure Julia stack. And so what's really doing the code translation under the hood is that you can run these symbolic variables through your functions, and it generates symbolic versions of your functions. And Yingbo will show how this lets you transform partial differential equation codes into codes that are then generating functions that are parallel, that are for sparse matrices, and all these nice little tidbits. So one last thing before getting into this is that actually we'll come back to this in a second. Instead, let's kind of start the Yingbo show here, where he'll take this and he'll start showing you how to really start coding with Symbolics.jl.
Hello, let me share my screen. Yes, hopefully this is working. So first of all, let's set up the environment. And in this environment, I have differential equations, modeling toolkit, plots, rewrites, and symbolics. So first, we can define two variables, x and y. And then to build symbolic expressions, we can build symbolic expressions by evaluating symbolic variables like this. So now we have the expression x squared plus y squared. And of course, the most simple symbolic operation that we can do on this expression is differentiation. So we can do it by symbolics dot derivative of this expression with respect to x. And then, as expected, the partial derivative with respect to x is 2x, right? And then, of course, you can compute the gradient as well. And then remember, the gradient is a Rn to R function. So in here, this function is Rn to R right now. And as expected, that's 2x and 2y. So if we have a Rn to Rn function, then we can use the Jacobian to compute the Jacobian matrix. So for instance, this would be the Jacobian of this array expression, right? And then as expected, the Jacobian must be upper triangular because of the incidence. Now I kind of want to get into another basic symbolic operation, which is substitution. You can do it by the substitution function from symbolics. So for instance, if we have sine of x squared plus 2 plus cosine y squared, and then we replace all the x as y squared, then substitute, sorry. So you can use the substitute function to substitute all the x variables to be y squared. And then we can also substitute in a numeric value, which is equivalent with evaluating this symbolic expression. And then, of course, because of the Pythagorean theorem, sine of x squared plus cosine of x squared must be 1. So plus 2, that would be 3. So that works as expected. Of course, we can do simplify as well. So simplify would simplify this expression into 3 directly. Sometimes it takes a while to pre-compile. Okay, so now we know the. So not only we do simplify by using the simplify function, we also do simplification during term construction. So let's say if we have the term 2x minus x, that will directly simplify to x. So it wouldn't, the expression wouldn't be 2x minus x, because we know this is just directly equals to x, right? And then this constructor level simplify not only works on simple variables like just x, it also works on expressions. So if I define a relatively complicated expression, so this would just be this is equivalent with 2ex, right? And then we also have constructor level simplify on division. So ex divided by ex would just be 1. And then ex squared divided by ex is just going to be ex. And then we can compute, we can compare terms using the is equal function. Oops. So yes, so this whole thing equals to ex. Then, so in this example, we are always using symbolic variables to trace into the expression. So in here, we have the expression x squared plus y squared plus sine of x. And then the symbolic expression is exactly the same. But then sometimes maybe you don't really want symbolics to trace into the function. For instance, if your function has some randomness or stochasticity, then you probably don't want to do it. So for instance, if I have x multiplied by a random number plus y, then you will run into the XKCD problem, right? So if I have full of x of y, and then I do symbolics derivative of this expression with respect to x, that would just be always this number. It wouldn't be a random number, right? Even though this number at the first evaluation is random, but then it would just be a fixed constant because we have already captured it in the symbolic tracing. So in here, you would want to use the register function from symbolics, followed by the function signature. So this is basically a way of telling symbolics to not trace any further. So in here, if I have symbolics dot derivative of full of hypot of x and y of y with respect to x, you will see that now because symbolics doesn't know the symbolic derivative of the function full, the derivative with respect to x on this function is left unexpanded. So by default, all the variables have the symbolic type of real. So all the so x and y in here behave like real numbers. So you can get the number type. So this is kind of like in details. You can get the symbolic type by using the same type of this of the internal representation of x. Oops. Yeah, so it says it's a real number. We can also instantiate variables with that has the complex type. In here, if I do z squared, then it will trace into z squared in terms of real numbers and then imaginary numbers. And then we can get the real part of z squared from that. Also, we can do a z conjugate z, which is, as expected, it's just going to be the length of the complex number. So even without taking the real, that would be just a real number. Right. So not only we can specify scalar valued symbolic variables, we can also have array valued symbolic variables. So in here, if I use this syntax, it's basically saying that xx is a symbolic array variable that you can index into. So you can index it into it by integers through 1 to 10, and then we can also compute the summation of this. But by default, the summation is going to be lazy, so we don't index into xs and then sum them one by one. But then it's a map reduce operation. So the map is identity, and then the reduction function is the plus symbol. And then the initial value of the reduction is false, which is another way of saying 0. So this is just saying it's a lazy representation of the summation operation. If you don't want it to be lazy, then first you can collect xx. So now you get a vector of num. So num is the symbolic scalar. And then we can call the sum function here. So this will be eagerly evaluating the summation of all the scalar valued symbols. Okay. So now let's dive into a more realistic example. So let's use the Rosenberg function. Rosenberg function is usually a nice test example for optimization solvers, and then it has the minima at the vector at the one vector. So let's Google the symbolic expression of Rosenberg function. So the Rosenberg function is defined by this expression, and then and then we can code it up in here. So Rosenberg. So these are the I indices. It goes from 1 to the length of x's, and then it has the index I. And then we do 100 times x's at index I plus 1 minus x at index I square, and then the whole thing square plus 1 minus x at I, and then this whole thing square. Now let's define n is 100. So, yeah. So to test this function, we know that this function has the minimum at the one vector, right? So if we do Rosenberg of xx at a variable with just once, oops, it's a bounce error.
You accidentally use x instead of xs.
Oh, right. Sorry.
In 2 spots, yeah.
Yep. Yeah, as expected, that will be 0. And then to verify this is actually a global minimum, we can perturb this variable by a little bit to verify that our implementation is correct. Yeah, as expected, that's a number that is greater than 0. So if we have a even larger perturbation, the function will take a even larger value. Now, so first to use, now we want to symbolically trace into the Rosenberg function, right? So we can do, so this n can be a runtime value. So n is declared here, but then we can use it in the ith variables micro still. And then we can do Rosenberg of xs. And then this is the whole symbolic expression of this function, everything unrolled. So currently, the support for array variables is not very extensive. So a lot of, in many cases, you want to expand the lazy representation of the array valued symbol into a eager representation of the symbolic value. But we are going to improve symbolics on array symbolics later, so you don't have to call the collect anymore. So to compute the gradient of the Rosenberg function, we can use the symbolics.gradient function. So of course, we want to trace it first. Rosenberg. With respect to the vector x's. Yeah, so now this is the symbolic representation of the gradient. So gradient is often used in optimization algorithms to do gradient descent or doing quasi-Newton. And then if you are using a full Newton solver or Newton trust region solver, you would also want to have the Hessian of the Rosenberg function. And the Hessian is just the Jacobian with respect to the gradient. So the heights, Hessian, the gradient. Oops. Yeah, sorry, give me a second. Oh, right. Yeah, of course. This is the, Hessian should be called on the symbolic traced function that is a Rn to R function, right? But then the gradient is a Rn to Rn function. So of course, in here, we want to call the Jacobian.
Yeah, so the thing here is that the Jacobian of the gradient is the Hessian.
Yeah. Hessian is the Jacobian with of the gradient, right? Yeah. So you can see here the Hessian is mainly 0, right? So it's kind of wasteful to compute derivatives, but just evaluate it to 0. We can take advantage of the sparsity information by using the sparse Jacobian function. So in here, it will give us a sparse representation of the Hessian. And then, of course, this sparse Hessian matrix is still symbolic valued. So each non-zero entry is a expression, a symbolic expression. Okay. Yeah, and then if you don't really need, if you are only interested in the sparsity pattern, but not the exact Hessian values, then you can use the Jacobian underscore sparsity function. So sparsity function is a Boolean sparse matrix that only has true and false entries. True entry meaning it's a non-zero entry in the Hessian. So just for fun, we can plot the sparsity pattern of the Hessian matrix. Yeah, you see in here, it gives an error saying blah, 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 none. So basically, this is saying that plot doesn't really know what to do with the symbolic valued entries. So remember that the highest sparse is a symbolically valued sparse matrix. So it doesn't really know what's the numeric value of it. So to plot the sparsity pattern, we have to convert it into arrays with only zeros and ones. So we can do it by broadcasting. Yeah, so this is saying if that is 0, then that's true, right? But then we only want to plot the non-zero entries. So we add a negation in front of it. And of course, we need to also broadcast the negation operator. So there's a dot in front of the negation operator. And then, of course, as expected, the sparsity pattern of the Hessian of the Rosenberg function is a banded matrix. Of course, we can also just simply put the highest sparsity in here as well, and that will just work. So let's try a few benchmarks. Let's try to run a few benchmarks on all these functions. So Jacobian versus sparse Jacobian versus Jacobian sparsity. So we can use it. We can use the benchmark variable. I benchmark micro to do the benchmarking. And then because grid and xs are global variables, it's more accurate. So the benchmark is going to be more accurate if you interpolate those global variables into the expression. So we expect that this is going to be the slowest because this one doesn't take any advantage of the zero entries, right? So this one takes about almost 400 milliseconds to evaluate, and then it uses around 15 megabytes of memory. And then sparse Jacobian, remember, sparse Jacobian gives us a sparse representation of the symbolic Jacobian matrix. So this actually doesn't evaluate, it doesn't try to take the derivative of a known zero entries in the Jacobian. So this is much faster than the previous evaluation. It's about 10 times faster. And then if you don't really need, if you don't even need symbolic representations of the Jacobian, we can just use the Jacobian sparsity pattern to get a symbolic, to get a sparse matrix with only zeros and ones. So this one should be the fastest because it doesn't even do symbolic differentiation. So in here, it only takes about 7 milliseconds to compute the whole thing. So remember, even before this whole optimization, it took about 400 milliseconds. So analogously, you don't have to take the first taking the gradient and then take the Jacobian later. We also have the Hessian function in Symbolics, so we can replace all the Jacobian by Hessian, and then of course replace all the grid with what was the variable before? Yeah, RXS. So replace all the grid by RXS. So Bayesian basically first takes the gradient and then evaluates the Jacobian. So this one should be a bit slower than the Jacobian function, right? And then sparse Bayesian is going to be also a bit slower than the sparse Jacobian because it has to check some linearity conditions to detect the non-zero Bayesian entries. And then finally, Bayesian sparsity is also like Jacobian sparsity, where it only returns a sparse matrix with only zeros and ones to denote the sparsity pattern of the Bayesian matrix. Yeah, so as we can see here, without taking oops, sorry. So without taking the advantage of the sparsity pattern, it takes about 600 milliseconds, and then with sparse Bayesian, it takes about 400 milliseconds, and then just computing the sparsity pattern, it takes about 100 milliseconds. So now that we have the Jacobian, the symbolic representations of the gradient and the Bayesian matrix, we can also use the build function in symbolics to generate Julia functions that actually evaluates the gradient and the Jacobian or the Bayesian. So we can use the build function from Symbolics to do that. So the first argument is going to be the symbolic expression that we want to evaluate using this function, and then the second or the rest of the positional arguments must be the inputs of this function. So the input of this gradient, of course, is the axis. So so the first returned function is the out of place function. So it just returns the gradient directly. And then the second argument, the second return function is the in place function, where it actually updates the first argument to the function. So I will demonstrate that now. By default, it gives us a huge Julia expression, but not a runtime generated Julia function, right? So users need to use the eval function in Julia to evaluate that to a actual function. But then we also provide the keyword argument of that is expression equals to false. So this is basically telling Symbolics to just generate runtime generated Julia functions directly, but not the Julia expressions.
Yeah, and the reason for the runtime generated functions is because if you just use eval and you're doing this inside of a function, right, you'll get that classic world age error, et cetera, et cetera. So this lets you be able to build you can compute these symbolic expressions and you can build them inside of functions. And if you use this expression building that we have inside of there, it will interact with Julia's compiler in such a way that you won't run into issues.
Yep. So to evaluate the in-place function, so first we need to have we need to allocate a vector that this function writes into, right? So that's going to be a vector that is similar to the input. And then we evaluate, let's name it AA, so we are not colliding variables. Then here, the in-place function returns nothing, but then you can see that the out vector is filled with the gradient values at the A point. And then the out-of-place function just directly returns the gradient. And as expected, they should be the same, right? Oops. Yeah. Yeah, and we can see that is actually the case. And then we can also validate our Jacobian, the gradient evaluation by checking it with forward diff. So it's using the forward mode AD to compute the gradient values. It's building block at the point AA, and then I'm using approximately equal here because actually I haven't tried to use equal. Let's see. Yeah, so that so our computed result is correct. But then if we check it using the exactly equal, then that would be false because the evaluation ordering is a little bit different. And then because of this difference in the evaluation ordering, it will result in some difference in machine epsilon. So remember that we are doing symbolic some symbolic manipulations already when we are constructing the expression. So if I do y plus x, that will actually return x plus y. So there is some ordering by default. And then because of this alternative ordering, it could result in some numerical differences in the order of machine epsilon. So not only we can generate functions that evaluates to a vector, we can also generate functions that evaluates into a sparse matrix. So this is a sparse representation of the Hessian matrix. And we can put it here. Yeah, so take a note in the in-place version of this function. So you can see that we are only filling the non-zero entries of the sparse matrix. So indexing into a sparse matrix by the Cartesian index. So in the form of ij, it's actually much slower than directly indexing into the non-zero entries. So by default, we build functions that assumes the sparsity pattern and then only fills the non-zero entries instead of doing the slow Cartesian index.
Yeah. So the one major thing right there is that is code that's going to be like an order of magnitude faster than the one that you might write by hand, right? Just because it's doing all those little tricks, and then you could also make it automatically parallelized and everything. So this already shows a pretty nice use case of Symbolics.jl.
Yep. So let's also evaluate the autoplace function. Autoplace at the point AA. It just gives us a symbolic matrix, and of course we can also do the in-place function. So remember that the in-place function actually assumes the sparsity pattern, right? So we need to actually use a matrix with the same sparsity. So we can use the h-out. So we use the similar function to build a matrix that has the same sparsity pattern. We can also use the sparse. Okay. So now this matrix, the sparse matrix has the element type of float 64, and then we can use HIP to fill this at point AA. Yep, and then we can compare that out should be the same as the Yeah. So there's some like a machine epsilon difference. Oops. Oh, sorry. I typed the wrong variable. So HOP should be the same. And let's see if it's actually the same. Yeah, that should be the same. Right. So we can also check the our symbolic Hessian with the Hessian computed by forward diff at point AA. That is approximately equal to HOP. Yeah, you can see that's correct. So now let's do a more realistic example of realistic use case for symbolics in the example of solving a 2D reaction, 2D diffusion reaction PDE. So to find a nice test example for Steve solvers PDE, we can find this example in Hire2, the book, the book by Hire on Steve solvers. And then we can use the example here that is the Bratz 2D. Yeah, it's this one. Chris, do you want me to code this live, or should I?
I think it'd be fine to copy it over. Okay. So yeah, so I mean, what Yingbo is going to copy over here is just going to be a discretization of that partial differential equation. You can think about it as just a really big ODE model if you don't know where that would come from. But it's like this ODE model written with loops and all these little nasty things in there to handle boundary conditions and all that.
Yep. So in here, there is a source term, and then this is the two-dimensional Laplacian. And then this is these are some nonlinear reaction terms. And then the boundary condition here is the periodic boundary condition. So basically, if so the left edge is the same as the right edge, and then the above edge is the same as the bottom edge. And then these are the initial conditions. So without using symbolics to accelerate it, by default, so this would be the pure Julia code of solving the Brotlater PDE. So evaluating this, evaluating the solve for the first time takes a little bit to compile, but then the actual runtime should be on the order of 3 or 5 seconds. Maybe because of the streaming, it will be a bit slower than that.
Yeah, I think the streaming is eating all your cores.
Yep. Yeah. So under the hood is using the BLAST library to actually solve the nonlinear system. So it's implicitly multi-threaded. So let's time this. Okay, it takes about 4 seconds. So to utilize the symbolics framework, of course, first we need to trace into this function. So now we instantiate a array-valued symbolic variable that has the same shape as the initial condition of the PDE. So remember, this is a PDE with reaction PDE with 2 species, and then it's a 2D PDE. And then our discretization size is 32. So this matrix is this array is 32 by 32 by 2, right? And then this whole PDE is also time dependent. So we also need to instantiate a symbolic time variable. So first, we need to collect the symbolic variables to make it eager, and then we call similar on U for the write-only variable. Because this variable is write-only, we don't have to initialize this matrix. Now we just call the right-hand side function of the PDE. So it is the definition of the PDE on the symbolic expressions with appropriate parameters. So here is the fully traced version of the PDE discretization. As you can see, that is rather complicated. So because this expression is so huge, so the size of this expression is so the size of this expression is on the order of thousands. The Jacobian would be 2000 by 2000, right? So it will be a huge Jacobian. So in here, we are only interested in the sparsity pattern of the Jacobian. We can just use the Jacobian sparsity function to evaluate the sparsity. So the first argument is the PD definition, right? And then the second argument is the input. So it's pretty fast. And then you can see that the diagonal non-zeros are from the Laplacian term. So that's the diffusion term. And then the off-diagonal patterns are from the nonlinear reaction terms. So that are these terms. Right. So to use this to accelerate our solvers, we'll just tell the ODE solver that the Jacobian prototype has this sparsity, and then because when we are solving this PDE, we are using a float type, right? So we need to convert the sparsity pattern to have the float type. So it has the element type of float 64. Then we can add this information to the right-hand side definition using the ODE function. So let's try to time this. So the first time is gonna also time the compile time. So this will take a bit.
And yeah, and I mean, when we come back after the break, I'll show how to do this directly with Modeling Toolkit, right? So you'll, for now, what we're showing is, oh, here's how you do all the little pieces. Here's how you calculate sparsities yourself and all that. If you wanted to do all the details, right? Modeling Toolkit will then take this and then do this automatically, kind of behind the scenes. But it's good to see it once.
Yep. So let's time it the second time, and that takes only about half a second. While the unoptimized version takes about 3.5 seconds. So now we just get a how much exactly? a bit over 5 times speed up, right? Of course, after any optimization, we should remember to check that our optimized result actually agrees with the unoptimized version, right? Because if it's incorrect, then the optimization is just wrong, right? So kind of like I expected, the sparsity, the version with, that utilizes sparsity gives the same solution at the end point. So just for fun, let's also plot the PD so that we know what we were dealing with before. So let's use the plotly so we can interactively see the solution. So here's the solution at time 1.4. Yep. So you can see that there's a little bump in the bottom surface, right? And then there is the above surface looks rather flat. Oops. Well, that's yeah. I haven't seen this before.
Yeah, well, it looks like Plotly grabbed your computer, but this is right where we're going to do the break anyway. So,
yep.
So yeah, what Yingbo showed then is that you can use symbolics to be able to kind of think about it as your calculator, right? It's your little math helper. It can, if you wanted to do all these derivatives and write out sparsity patterns for your function and everything, it can take your code and then automatically turn it to sparse. And the functions that it'll build are these big non-allocating things that are doing all the tricks that are required to make sure that it's the fastest code possible. So we'll do a short break now and revel in our speed wins. But when we come back, I'll show you how to do this with Modeling Toolkit, where we start to just say, well, here's the ODE system and sparse equals true, and it'll be doing these kinds of things under the hood. So we'll come right back and we'll do the Q&A session right once we get back. All right, We're back, and now let's go through and triage a few of these questions. So, is there a way to use optimization solvers within MTK like it's done in JUMP? Or can the expressions obtained with MTK be passed to JUMP as constraints? So yeah, so I'll mention in a little bit actually that Galactic Optim is a library for optimization, which you can use all of JUMP solvers, right? It can use the MathOpt interface, and so we have an interface to be able to use this to kind of generate code for JUMP solvers. Yeah, so that is true. It is still a little bit kind of in development. So I mean, we're not going to be focusing too much on the optimization side of the story, but yes, this is a very nice way in the near future to be able to do code optimization for nonlinear optimization. Right? We're focusing really on the nonlinear world here. If Symbolics can generate C functions and Modeling Toolkit has symbolic description of the models, could Modeling Toolkit also export their models to C? Yes, indeed, it can do that. I will say that the C code generation is still very kind of primitive right now. So it can handle the things like multiply and plus, and some math functions from the standard math library. Can't handle all of them yet, though. Someone needs to actually go in and handle a few more of these cases. What do you do with the gamma function and things like that? Someone needs to know how that translates over to C. But once all those are handled, then those would be done well. Let's see. Can Symbolics do a cross or dot product between two sim arrays? I'm not sure if it can right now, right off the bat, but that's because as Yingbo mentioned, the symbolic arrays are kind of still in development, and so you can, if you scalarize them down, using collect, you can then do dot cross product and all that fairly easily. Definitely in the near future, we are going to be doing a lot more with making sure that there's a lot more coverage of array expressions in there. Can you make a symbolic array with a length specified by a symbolic variable? Let's see. I don't think that one's finished, right?
No. So currently, we basically assume quasi-static, right? So the size of the array must be a concrete number instead of a symbolic integer. So otherwise, a lot of checks would not be terminating, right? Because we have no idea what the final size of the array is going to be.
Mm-hmm. Yeah, so you mentioned the symbolic simplify can be solved, but introduce an approximation area different from the original system. Is the symbolic transformation not exact? So this comes from floating point errors, right? So if you do x plus y plus z, you do not necessarily get the answer of x plus z plus y. That's just something to do with floating point. And so what Symbolics.jl generates might not be exactly what automatic differentiation generates. And so that's why when doing the approximate, when doing the checking the result, it's approximate equal, right? So that's just a little floating point thing. Mathematically, it's the same function. Floating point wise, it might be a little bit different based off, up to like 10 machine epsilon or something. Yeah, we'll get into a lot of these other modeling toolkit questions in a little bit. I'm trying to see if there's any that's more symbolic here. So are the Jacobians generated by AD or symbolic differentiation? So the same tools that are underlying the Julia AD libraries are what's used to define the derivatives and gradients and all that in Symbolics. So it turns out that if someone has given a scalar rule for how to take the derivative of a function for automatic differentiation, then Symbolics.jl can actually do it the same way, right? It actually uses the same rule set. But it does something very differently for how it does the actual calculations, right? It's generating an expression and then building Julia functions for that expression. There's trade-offs between the two approaches, right? So automatic differentiation will not need to build out these expressions, and so it'll scale to really large equations in a very nice way. It also will handle cases that Symbolics cannot trace. I'll mention the quasi-static case in a second here. So there are some things that AD will work on, the symbolic differentiation will not work on. But symbolic differentiation, as Yingbo showed, it can do a lot of specializations on things like sparsity patterns in ways that automatic differentiation cannot, right? Automatic differentiation can do forms of sparsity handling, but those are not going to be as optimal as directly handling all of the all the values of the sparsity pattern, individually. So if you have these very large sparse models, symbolic differentiation can give a lot of nice gains over that, though automatic differentiation can handle these other cases which symbolic differentiation cannot. So they're really complementary tools. And we throughout the differential equation solvers and throughout SciML, we use both of them in their respective places. I think that's going to be most of the symbolics equations. Oh, there's one. Does substitute not work with symbolic arrays? Symbolic arrays does not support a lot of things at this point, though that is going to be one of the things that Shashi's working on over the next few months. And I think that there are, those are most of the questions. So one question that I do want to walk through is will this support integral differential equations? Yes, support for integral differential equations is almost merged. I'll show an example with the neural PDE solvers, and the neural PDE solver will be able to handle the integral differential equation cases. So yeah, even weird, fractional differential equations and all that can be symbolically expressed through the system, and then you can handle it and solve it through some of the solvers as well. So I won't mention too much more on that case. So I'm going to kind of leave that dangling, see the documentation and see the release announcements when that comes out at the end of the summer. But all those kinds of cases are what we are working on now. Now that the simple ODEs are all good. So let me get back to the screen share here.
By the way, so I kind of also want to cover this interesting question about EX divided by EX.
Oh yeah,
is problematic if EX can be 0, right? So my rationale is that because we know symbolically it's the same expression divided by the same expression, right? Now we have a removable singularity at that point. So we will just define that point to be 1. If you are aware of some use cases where that is actually problematic, then let me know. But for my experience, I just haven't seen anything that would be actually problematic, because we already know that the two expressions are exactly the same, right? So you can take the limit, and then the division is defined.
Mm-hmm. Yeah, so in terms of actually as a symbolic numeric modeling tool, right? That's the assumption that you'll want to make when you're doing this in an ordinary differential equation, when you're doing this in a nonlinear solvent. So that's the assumption that the library is able to make in these cases. Definitely, there might be some kind of weird mathy case where you don't want the limit, etc. But if you have a case, then you can show us. Now, all these simplification rules, constructor rules, and all that, they're all based off the types. And so you could create a safer real floating point type that has different algebras defined on it that wouldn't simplify that. So that's the reason why Symbolics has this whole type system, because you can make more assumptions in some cases, you make different assumptions in other cases, and you can choose which assumptions you're working with based off of the types of the symbols. So yeah, before we get back into some of this other discussion, I do want to say, let's if you haven't done so, show the support for the libraries by hitting that star button, and also thank all of our sponsors and everyone who's helped us out to build all this. So before we move on from Symbolics.jl, I do want to mention one last little point with it. So we mentioned very briefly this, quasi-static model. So, I really recently wrote a blog post on this, and I want to kind of mention a little bit more about this, right? Because, what are things that can be handled by the Symbolics.jl library? It's equivalent to, ModelingToolkit can only handle things that are representable in Symbolics. So what can Symbolics represent, right? So it turns out that if you have things that can, in some sense, be represented as a mathematical function, those are all the things that can do that, right? And, I mean, that's a vague way of saying it, but here, for example, is a loop, right? But if you think about what this loop does, it's always 2 times 2 times 2 times x. it doesn't matter what the input value into the function is. It's always the same computation. And so this is something that's traceable. And Symbolics.jl will tell you that this expression is 8x, right? This is something that's not traceable, right? Because if x is less than 3, it uses this code. If x is greater than 3, it uses this code. The actual code that you call differs based off of the input value. And so what is your compute graph? Like, what is your symbolic expression in that case? Well, there is no one symbolic expression, right? There's two different things that can be computed. And so what you want to use instead is you can use the traceable syntax like if-else.if-else, right? So this is a way of representing this in a symbolic way, such that it's always calculating the same thing, right? If you think about this as a Julia function, it'll always calculate all of the arguments to the function before it checks which one to use. And so the answer can be different depending on x. But this has one set of computations that are always done, and therefore this is a static, this is representable in a static way, and it's traceable. Now, there are some functions which are not able to ever be changed into a static representation, right? Like how do you do factorial of x? Well, factorial of x, when x equals 6, it's 6 times 5 times 4 times 3 times 2 times 1, right? When x equals 7, it's 7 times, so the actual number of things that you multiply by, the symbolic representation of factorial changes depending on what value you're taking the factorial of, right? So symbolics, there is no way to represent that in a static, here's your mathematical expression, because your mathematical expression differs based off of every value that you'd want to apply it on. And so this is not representable. And if you try to trace through this in Symbolics.jl, you'll get an error. It'll tell you num, Boolean, et cetera, et cetera. There's a frequently asked question answer in the documentation about this case. So what do you do if you do want to handle factorial? Well, notice that, inside of Symbolics, sum works, plus works, multiply works, sine works, cosine works. All these things work by default, right? But it's all built in Julia, so you can extend Symbolics.jl at will as much as you want. So you can say, here's my factorial of x, at register it, right? So make it something that we don't trace through. So this is now a function that has been added to Symbolics.jl, and it will just keep it as this closed function, and it won't try to find out what's going on underneath it. And so this is a way to be able to handle these non-traceable codes in a way. You just register it. And if you look at the documentation, you could define, if you know the derivative of the function you registered, you can define its derivative, and et cetera, right? Everything in Symbolics.jl is just on the Julia side using at register. This is no different from what's actually built in the library. So you can extend it and you can add derivatives and everything, and it's no different in usage or performance from what's built in. So that's Symbolics.jl, right? So that's how you move around in Julia with this new symbolic library. Now let's get to how you do symbolic modeling of ordinary differential equations, right? So now let's start to do these examples, which I kind of went over briefly. Let's do these examples live, right? So let me actually pull up my codes here. Let's see. All right. So let's start by defining an ordinary differential equation, right? Let's take this example from here, where we want to do the second derivative of the first equation, and first derivative of here and here. So what I'm going to do is it's going to look a lot like Symbolics.jl, because half of it is Symbolics.jl, right? I'm going to say using Modeling Toolkit and differential equations, right? Then I'm going to say, well, the parameters of my model are t, sigma, rho, and beta. Right? And you can see that we represent these just as these symbolic parameters, right? And so what happens here is, Symbolics.jl has this idea of a variable, but this variable can have metadata. So this adds metadata to say, oh, this is a parameter, not a state variable. Treat them differently. When you build the ODE, it'll automatically separate these out for you. But now let's build some of our standard variables. Let's build some state variables. We have x of t, y of t, and z of t. right? I'm saying that these are variables that have a time dependence, so that way when we do things like calculate the derivatives of them, they're not dropped off automatically, right? They are. It's known that these variables have a time dependence that we have to be aware of, right? And when we go to partial differential equations, you can say like, oh, this one is a function of x and t, and this one's a function of only t, right? So you have these variables with dependencies, so that way we can do the chain rules correctly. Now let's say that d is this differential operator with respect to t. And so what d of x means now is this means take the derivative of x of t with respect to t, right? This is another way of saying dx dt. So let's write out some of our equations. So my equations are, let's say that it's d of x. There's a shorthand way of doing that where you can say this is derivative squared. I won't use that for now. I'm just writing out a form of the Laurent equations where there's also a little trick to it. And the reason why I'm doing these equations is because I know it makes a really pretty picture. And my pretty picture function's almost done here. And there we go. Now this is an array of equations, and these are our equations, right? The second derivative of x with respect to t equals these equations. The first derivative of y with respect to t equals these equations, right? And this is just how you read it off. You always think about this tilde as an equal sign. Why do we not use equal sign? Well, because if Julia allowed you to overload equals, then all hell would break loose, pigs would fly, and etc. So we use tilde as our equal sign. All right, so now let's tell Modeling Toolkit that this is an ODE system. Right, so the ODE system of our equations, and here we go. It says, it knows how to say that this is our states, and remember, these are our parameters. It figured that out from our metadata. And what is our model? Well, you can check the equations of our system, and it should match the equations that we wrote down, right? Let me make this one step bigger. Yeah, and so this does match the equations that we wrote down, right? But the ODE solver will want this to be in first order form. So let's I mentioned before that we had this little transformation going on, right? Where the way to be able to solve a higher order differential equation is to say, well, let u prime equal x, and then x prime equals, u double prime. And so if x prime equals u double prime, then x prime equals f of u, right? This is a trick. If you haven't seen it before, you can, work it out by hand a little bit, but you don't need to do that yourself, right? Because, this will be handled. So let's try that out. So ODE order lowering of the system. This should give me a new version of the system, which has 4 equations, right? So this x sub t is this new variable that was introduced. That's the derivative of x. And if we check our equations, right, equations of the system, we see that it has 4 equations, right, where the derivative of x with respect to t is x sub t, and the derivative of x sub t with respect to t is our original second derivative term. Right. So it's now lowered this to a first order differential equation, which we can then solve. Right. So let's start to say, well, u0 equals d of x goes as, right. So since I have a higher order differential equation, I need to make sure I define my initial condition for both the value of x and its derivative. Right. I write down my other initial conditions. And now let's take a look at our parameters, right? So I'm going to say that my sigma parameter is going to be 28.0, right? And so one question that you might have is, well, why don't you just give an array of values, right? Well, the key here is that if we're going to allow Modeling Toolkit to change our equations around and add equations and all that, right? We can't really rely on indexing anymore, right? What's the third variable in our system now that we've added a new equation, right? Or our third variable is still z here, but our first variable was x sub t. So when you get to this kind of symbolic modeling, you do not necessarily want to be using indexing too much anymore. You really want to be using your symbols and start to say, well, let's, get the initial condition of x is this. So always, when you're using Modeling Toolkit, it's best to always talk about it in the symbolic form, right? But now let's build the ODE problem, right? Let's translate from symbolic back to numeric. And what we can do is we say, okay, we need a time span that we're going to solve this on. And now let's make our problem. This is an ODE problem where when you're using differential equations.jl, right, it would say, oh, this is where your ODE would go, right? But now with Modeling Toolkit, we say, let's just put our system in here and it will handle everything for us. But what we do have to tell it is what's our initial condition, what's our time span, and what are our parameters, right? These are exactly the same arguments as using differential equations.jl directly, but now we're giving it these maps to understand how to translate under the hood these symbolic variables into initial conditions and build everything for us, right? As a little note, I'm going to just say Jack equals true, right? Where Jack equals true is going to, what this means is it says, oh, build the analytical Jacobian function for us. We're going to need it in the solve, right? So you can say Jack equals true, sparse equals true, all the things that Yingbo is demonstrating with Symbolics.jl, you just tell it to do that under the hood and it will do this for you. And what do we get? Well, we get an ODE problem for differential equations.jl, which is now fully numerical, right? And now we take this and we just say, hey, differential equations.jl, do you know how to solve this problem with set 5? And it does. It says, here's a success. Here's the solution. It's just a normal differential equations.jl problem, right? But now, as I mentioned, you could go and look at your equations, right? Or you could look at states of the system, and this will tell you what the ordering of your equations are, right? That x sub t, so the first derivative of x is going to be your first one, y is your second one, z is your third one, right? So this tells you what the ordering of the solution vector is. But you probably don't want to be using that. Instead, what you can do is, so the symbolic library is really tied into all of the tools of differential equations in SciML at this point. So everything supports symbolic indexing in symbolic forms. So this is a trick that might make people pretty hype here if you haven't seen it. If I just say I want the solution with respect to x, well, here you go. There's the solution of the x variable, or here's the solution of the derivative of x. And it just spits out, this is the time series, right? Now you can also say like, well, I want to use the interpolation, right? So what is the value at time t equals 50 of y, right? And you can then tell it that use for the index by y and give me the value at the time point 50, right? And so this is actually a continuous function using the symbolic index to be able to find the right variable in here, right? And all of the tools then also support this. So if you go to plots, right, you might know about the plotting recipe for this for the differential equation library. This now all supports the symbolic variables. So if we say, oh, plot variable x against variable y, you make this plot here, and this is this beautiful mixture of Lorentz equation. This is why I like to choose this example. Right. So that's how this example really works, right? You define a second order ODE, you lower it down to a first order ODE, you define your initial conditions and your parameters, and you solve it. And lots of little things are happening under the hood. It's generating equations, it's generating Jacobians, it's understanding how to do the indexing by symbolic variables, and you just treat this as like your modeling little calculator. Now let's go to this next example. What I want to do is I wanted to find two equations and I want to stick them together. So let me do this here. So I'm just going to copy over some ordinary differential equations. So here is the Lorentz equations. I've used them so many times and so many. So you can look at other talks for where this is defined, right? And what I'm going to say is I'm going to have one ODE system which is called Lorentz 1. I'm going to have another ODE system called Lorentz 2. So these are, at this point, they're the same symbolic equations, but now I want to kind of define some kind of mixture between them, right? So let me say I have a new variable, a of t, and I have a new parameter, gamma. And what I want to do is I want to say, well, the connection between these models is I can give it any equation that I want, right? And so what I'm going to do is I'm going to define the connection by a algebraic equation. So this algebraic equation is going to be that the first, we use the x value from the first ODE system, and we combine it with the y value of the second ODE system. And then we define, we use our new variables in here. Right? And so this uses one value from ODE system 1. This uses one value from ODE system 2. But it also uses a new equation. So this equation will, if we already know these other two variables, that will uniquely define this new equation, right? Or this new variable. So let's pull this over then. Let's define our connected system. So our connected system is going to be this ODE system where our equations are connections, right? These are the new equations that we're adding. I'm going to just list out like what are the new variables that are in here. Right, so the independent variable, the array of the states, and the array of the parameters. I think you can let this automatically discover it, but I'm being kind of explicit to show the other constructors. And now what you can do here is you say, well, my subsystems are Lorenz 1 and Lorenz 2, right? And what this will do, let me drop this down. What this will do is this creates the set of 7 equations where I have one Lorenz system and a second Lorenz system and my added variable in here. And the full set of equations of connected is the full, it's these two systems together. So you have two independent ODE systems which are the same, and then you have the connection equations in here as well. Right, so there's your connection equation, there's our first ODE system, and then there's our second ODE system, right? And notice that there's this namespacing going on, so that way, Lorenz 1 has a variable named X, Lorenz 2 has a variable named X, but they're actually two different variables that we can reference. So yeah, let's then, I'm just going to copy over some initial conditions because this is a pretty long list, right? So we have to give the initial conditions and parameters for each of the each of the different variables, right? But other than that, it's going to be the same as what we did before. We define the time span that we want to solve this on. Then we define now we say, oh, let's translate this from symbolic into numeric by using the ODE problem, where once again, we instead of using an ODE function, we just put our symbolic system here, and then we tell it to our parameter maps for how to transform from symbolic into numeric. And now here we get a numerical system, right, that we can then bring over to differential-equations.jl. Right, so we solve this with differential-equations.jl. And then once that's done solving, then you get it is once again something that is indexed. You can look at what the equations are by checking your states of your connected. Right, so you can see like, oh, it's A and then Lorenz 1, Lorenz 1 dot y, but you don't need to use that ever, right? You can just say, oh, what's the solution of A over the time series? What's the solution of Lorenz 1 dot x, right? And it will just know how to translate from the symbolic variables down to giving you the right time series. Right, so all the things that you would do with differential-equations.jl, right? You would say, say that equals 0.1, and then when you do, Lorenz 2.y, this gives you the solution at 0, 0.1, 0.2, 0.3. This gives you the time series of Lorenz 2.y. Right, so this gives you a really nice way to be able to build independent models and start sticking together. And once again, all of the symbolic indexing works on the plot recipes as well. So let's plot the variables of A versus Lorenz 1.x versus Lorenz 2.x. Right? And when you plot these together, that's a little bit of a nasty plot. And here's another version. Right? And let's resolve this without save that, so that way we now have the smooth interpolation form. So okay, so those are some ways to be able to compose systems together, and it has this kind of namespacing system, so that way when you compose systems, you aren't overwriting or reusing names, right? So this is composing versus inheritance. You can check the documentation for what you do if you want to use inheritance instead. But now let's do this example, right? You don't have to use Modeling Toolkit to get the advantages of Modeling Toolkit. So here, let me pull this in. Right. Under the hood, what's going on is very similar to what Yingbo showed, right? Where here we have a function, right? This is a Julia function And when we stick symbolic variables into there, it can automatically translate it into the Julia function, or into the symbolic function, right? So here I grab the system, and if I ask it, what are the equations of the system? Well, the equations of the system are defined by these, here it has these parameters as symbolic, and it chose some names because this, it had to choose some names, and it kind of just captured our mathematical model here. It just captured this mathematical model into its symbolic form, right? And so all the things like, oh, how do we analytically calculate the Jacobian? Well, we can just regenerate this system and say, build it, and it'll build it in the fastest form possible. So it'll fix this allocation issue, but it also will build in this analytical Jacobian, and we'll just say, okay, let's do that, right? And if we solve this, right, let's use benchmark tools at b time sol equals solve the original problem, right? And we can check this against at b time sol gets solved the problem with the Jacobian, right? I'm not quite sure why VS Code is kind of doing some weird printing here, but yeah, so there is our first time, right? And now we'll do the second benchmark. And ta-da, this made it quite a bit faster, right? There's two reasons why it made it faster. One is because this version of the function is allocating an array, whereas the version that it generated under the hood, like what Yingbo showed, right, is it can generate these in-place functions, which are non-allocating. And so it's just a faster version of this, right? The other thing that's going on here is that it also built an analytical Jacobian, and it really took into account all the sparsities and everything, and built a really fast code for that. And so, those two reasons are the reason why it's faster. If you supply a really good Jacobian function, and if you wrote your function in a way that was fast in the first place, this might not be faster. So it's not like a trick that'll always make all code faster. But if you're someone who doesn't know a lot about code optimization, this might beat you. And if you're lazy, this also is just a good thing to know. Right? But here's another example for why you might want to be using this tool. Right, so let's go through this pendulum example. I'm just going to paste this over. So here is this pendulum that we defined, right? So it's a derivative here, and then for this pendulum we're writing in Cartesian coordinates. And so what we want to do is we want to say, well, the length of the pendulum is constant, right? And that's what's hard about this equation. This, we're trying to say that we have x in the derivative of x, y in the derivative of x, and the tension variable. And the tension should just be figured out by knowing that the length of the pendulum should be constant. But this is a higher order, this is a higher index differential algebraic equation because the this tension variable does not show up in this algebraic equation, right? If you don't know about higher index DAEs, then you probably should be using this tool, right? Because what will happen if you try to solve this, right? If you take this and you say, well, let's generate this ODE function. I use a mass matrix to be able to say that this has a constraint equation in the last equation. What does that mean, right? So mu prime equals f. If the last row of m is all zeros, then this is the same thing as saying 0 equals what's on the right-hand side. And so this is just a constraint equation, right? This 0 right here is basically saying x squared plus y squared minus l squared equals 0 is a constraint that I want to have on my evolution, right? If you haven't seen that before, check out the documentation. So this is this differential algebraic equation that has 4 differential variables and 1 constraint equation. And when we try to solve it, let's do this directly. Let's even use a robust method for stiff equations just to really show that it's just not even going to be able to handle this. Oh, wait. Oh, I forgot to put in the pendulum problem. Yeah, so it spits out this return code, right, which says dt less than min, and it shows this warning here, which says dt is less than dt min, right? And if you see this in differential-equations.jl, there's many reasons why dt can go less than dt min, but what it basically means is that your equations are probably exploding, right? You have something that you know, the adaptivity is trying to take dt smaller and smaller and smaller to be able to get less and less error. But what actually happens on a higher index DAE is that it doesn't converge. So as dt gets smaller and smaller, it's the error of the calculation isn't shrinking, and so it just gives up, saying, I don't know how to deal with this, right? So don't write your equation like this, or if you do write your equation like this, we can translate it to Modeling Toolkit, right? We get this equations of the trace system. Right, so this is the symbolic form of that mathematical model we wrote down, right? And now what we can do is we can say, well, lower the index and do the structural simplify. This is being explicit. In fact, structural simplify will do index lowering as part of its pass. So you don't have to be explicit about that. But here I just wanted to kind of show, like, hey, if you do this, you know, then it'll build this new system, you know, this pendulum system, which has different equation in the end here, right? This is mathematically it's the same exact model, right? It just differentiated the last equation twice and did some substitutions, but for some reason this thing is just much more stable to solve, right? And so it's really kind of automatically changing your code around, and so now we can, you know, build it back to an ODAE problem. I'll mention the difference between like ODAE problem and DAE problem and all that in a second, but we can then bring this back to a numerical code. And it will actually remember what your initial conditions and what your parameter values were, so you don't have to put them here again. And now this version is able to solve with a non-stiff ODE solver, right? It turned a problem that it couldn't even solve with a stiff ODE solver, and it turned it into one that it can solve with a non-stiff ODE solver. And there you go. There's your pendulum solution, along with the tension at each time point. So that, you know, so if you don't know why this kind of helped out the equations, then it's really kind of doing something really nice underneath the hood, which, you know, you can ask questions and we can go into this in the chat later. So what are all these different problem types? Well, in the ODE problem is always going to be an ordinary differential equation with a mass matrix associated with it. If you have a differential algebraic equation, this mass matrix is going to be singular. And whenever you have a mass matrix, you need to make sure you're using a method that is compatible with mass matrices. You can find that in the documentation. If you go to if you go to diffeq.sciml.ai and you look at the DAE solvers, it'll show you that, you know, these are the ones that are compatible with mass matrices, right? So one of the downsides of using ODE problem is that if you do have constraint equations, you do have to make sure you're using an implicit method that can handle the mass matrix. DAE problem is fully implicit, right? If you look at this uses special solvers like IDA, and you can look at the documentation for that specific case, right? So these are the ones that you might have known about before. ODAE problem is a really weird hybrid of them, right? Basically what it says is a DAE problem has constraint equations. So what we'll do is we'll build a new version of your function that embeds a root find inside of there. It actually embeds a torn version of the root find, so that way it's actually a little bit faster. So this actually gives you back a form which is simulatable without any mass matrices or anything. This is just a standard ODE problem, where whenever it wants, it can reconstruct all the algebraic variables on demand. So this is a form that you can only get symbolically, and actually requires that you've done structural simplify for that one to work. So yeah, so I showed ODAE problem here, though you could use DAE problem if you use IDA. You could use ODE problem if you use a stiff ODE solver, but ODAE problem actually simplifies it so much that it turns into a problem for a non-stiff ODE solver. So I now want to bring this back to Yingbo to be able to show how you do Acausal modeling in Modeling Toolkit. This is a special form of composing of systems to be able to build out these things like circuit models and HVAC models really quickly and get these really big models that then uses structural simplify.
Yeah.
So first, let's just Google what is RC circuit exactly. And so it's basically a circuit where there is a voltage source, and then there is a capacitor, and then they're series with a resistor, right? So you will say that, well, that's just a really simple linear differential equation, right? So why do we need to make it as a in a component form? Because so basically, if we write all the components out and then just simply connect them together, then we don't even need to think about how to write down the differential equation exactly. And Modeling Toolkit will just take over. We'll take that over for you. So let's first do using Modeling Toolkit. And then, of course, ultimately DGQ. So first, let's define the independent variable. So parameters, that is time. Then we need to think about, so when we connect two basic electrical components, right? The thing that characterizes the connection is just the voltage at that point, and then the current at that point, right? So we want to instantiate a connector that is called a pin, and of course, all the components should take a name keyword argument in it, and then it contains variables, voltage that depends on time, and then current that depends on time. Also, we can specify the default initial conditions. So we can just say default to 1.0. Great. And then, so each Modeling Toolkit component should return a ODE system. So in here, this is such a simple system that there are no equations, right? And then the independent variable is t. The states are voltage and currents, and then there are no parameters. Also, we need to pass in the name. Then we need to think about when connecting two equations, then when connecting two components, what kind of connection equations we need to generate. So we need to tell Modeling Toolkit how the way to generate connection equations by overloading the connect function on the type of pin. So basically, the connector micro may declare types pin in some sense, so that we can overload the connect function on the type pin. And then it takes arbitrary number of pins and connect them together. So the first would be the Kirchhoff current law, which is basically saying the summation of all the currents should be 0 in the connection in the connecting point, right? So the first equation is all the currents sum to 0, and then the second equation and then we need to write the Kirchhoff voltage law, which is to say that all the voltage equals together, all the voltage equal, right? So that is from 1 to the length of pins minus 1, and then we connect all the voltages. A plus 1, B, and then we return all the connection equations. So this is not explicitly denoted in here, but then we need to declare a ground component. Otherwise, everything in the inner circuit is speaking in relative terms, right? So the circuit is only defined by the voltage differences, but then there's no definition of where the voltage is actually 0. So to make this system have a unique solution, we need to declare a ground component. So all components takes name, and then we can use the named micro to. So yeah, let me explain how the named micro work. So we declare the positive pin, so basically the positive terminal and then the negative terminal. And then, of course, it has the, sorry. Actually, in ground, we don't have positive and negative terminal. It's just the ground pin. And then the only equation is the voltage of the ground is 0. And then because ground contains this ground pin, we need to use the compose function that composes the ground component itself and the ground pin component. So that is from pin.
Yeah, so compose is basically, right, I mentioned that, we have ways to be able to do composition and also inheritance, right? This is that kind of technique. Instead of just saying it's a subsystem, right, you can say, well, let's build the system that has these two pieces together, and that's what this compose primitive lets you do.
Right, and then the named all the named micro does is it's basically writing the same thing as name equals to G, but the symbol G. So that this is quite redundant. So we just made a micro for doing this.
Yeah, yeah. One of the all these macros, right? At variables, at named, what they're really doing is they're making it so that way the names of the symbolic things that are computationally happening match the names that you actually have in your Julia code, right? In theory, they can actually be different names. And when you are when you're using this to actually build libraries and stuff, you might want the name from the user, right? And so the names do not necessarily need to match the Julia code, but when you want that to happen automatically, right? That's when you're using all these macros.
Yep, and so okay. Let me finish typing. P.V minus. So one port is in some sense a abstraction of all the simple electrical components. So this basically only declares the boundary conditions. So simple electrical components, the voltage of this component is basically going to be the voltage drop between the positive terminal and then the negative terminal, right? The negative pin and positive pin. And then this simple electrical component should not have any current storage. So all the current comes in, comes out. So that's basically saying positive current plus the negative current sums to 0. And then the current of this component itself is the positive current, right? Because there's no current storage. And then we return the ODE system with the equations, states. And then no parameters. Oh, right. Independent variable states and the parameters. Of course, the name. And then don't forget to compose the positive pin under the negative pin. So basically the same reasoning as the ground. One port contains 2 pins, so these are the 2 sub systems. Then from this one port, we can extend this one port to basic electrical components. So basically the capacitor and then the resistor. The resistor is easier, right? The resistor is basically saying that the current is related to the voltage with the resistance, right? So resistor. And then the resistor should take a parameter value that is the resistance, and then let's default it to 1. Port. So resistor is basically a children of, in some sense, a children of one port, right? It inherits all the equations and all the states from this one port. And then because it's an inheritance, and then we want to force them to use the same variable. So in here, if we do g.v, sorry, yeah, let me actually evaluate this. So if we just do p.v, then it returns a variable that is namespaced, right? So basically, the v variable and then the v variable that we got from this get property are different variables, because after the get property, it is namespaced. The way that we get the v variable exactly is using the unpack macro. Oops. Yep. And then, so now we have the v that is exactly the same variable from the component p. So in here, because we want to share all the states and equations, we don't want to use namespacing, right? So we just do unpack. We want to unpack voltage and currents from this one port. And then the only equation that we need to add. So in here, we specified all the boundary conditions, right? Now we only need to specify the interior equation of the resistor, which is V equals to current multiplied by the resistance, right? That's the Ohm's law. And then we use the extend function that extends these equations with empty states and then a parameter. So remember that we have the parameter R, right? So we have parameters R that equals to R. So this is kind of a funny syntax. In the left-hand side, R is actually a symbolic variable that we define, right? And in the right-hand side, R is the default value for R. This is just a neat, I mean, maybe not so neat. This is just a cute syntax for basically writing something like this. So this is the default value for R. And then we now define the symbolic parameter R that has the default value Ri. But then this name is not so special. We can just make their name the same, right? Then we extend this one port. Now we just finished the resistor. And then capacitor is basically the same, basically follows the same logic. Oops.
Yeah, and just to mention it again to emphasize, right? The extend means, you know, that is inherit all the variables that the other ODE system had, but add this equation to it, and versus the, you know, treating things compositionally.
Yeah. So this is the capacitor equation, right? Now we basically finish. Oh, oops! I missed to specify the name. Yep. So so basically, capacitor has the parameter of the capacitance instead of the resistance, and then here is the interior equation for the capacitor. Now, basically, finished all the hard work of defining components. Now we can say, let's instantiate a RC circuit with resistance equals to 1, and then capacitance equals to 1, and then, oh, sorry, I missed one thing. So we also need to have a component for constant voltage source, right? This is not shown in this diagram. So basically, we need to have a battery for the RC circuit. Otherwise, it doesn't quite make sense, right? So we need to have a constant constant voltage, yeah, that has the parameter V. So constant voltage is basically battery. So battery is also a simple connection, simple electrical component. So it's a it's a child of one port. So in here we only need the voltage, right? And then we have the voltage parameter. So the only equation is the voltage of this component equals to the voltage of the battery, right? So think the constant voltage as an ideal battery. So
yeah, so if you haven't seen component-based modeling before, it really all that you're doing here is you're just saying like, oh, what's the law for the resistor? It's Ohm's law, right? You just write a lot of things that are true, and what you'll see happen is that it'll generate your model from all the things that you are saying is true.
yep, and then we can reinstantiate the yeah, spelling is not my thing. Capacitor. The voltage source. Voltage source. Also, don't forget the ground. And then the ground doesn't need any parameter. The capacitor needs the capacitance, and the voltage source needs the voltage. So now let's actually build the RC circuit. So now we want to write the actual RC equations. So because we have already, we already instantiated all the components. We now just need to use the connect function to connect them together. So in here we connect the positive terminal of the voltage source to the positive terminal of the resistor, and then we connect the negative terminal, the negative pin of the resistor with the positive pin of the capacitor, and then we connect the hard to get this. Yeah.
There is an astute viewer who noticed that all of your app parameters are missing an E.
Right. Yep. Yeah, and then we connect the negative pin of the capacitor with the negative pin of the voltage source, also the ground. Yeah, never forget the ground. Then now we actually instantiate the RC model. So compose can also take an array of subcomponents. So this RC model has subcomponents: resistor, capacitor, voltage source, and ground, right? So we just put them there. Source, ground. Let's just run this and see if it works. Oops, probably some spelling issues. D not defined, right. So because now we have the independent variable, right, we also need to define what, oops, not different equations. Different, did I spell that right?
No, that's spelled incorrectly.
Yeah. Oops, it's probably better for me to just, yep, autocomplete. It's easier, right? Yes, it worked. So there are 20 equations and then 20 states, so everything is balanced. We can actually simulate it. So before doing the simulation, so you will see that, well, now currently we actually have 20 equations, but then shouldn't we only have one equation? Like this? Yeah, and then you'll be right. So basically, we just need to do, so let me just type here. We'll simplify this RC model. And the first time always takes a bit.
Yeah, at least we can say that with Julia Sim, we're going to be building this into the sys image, so that way it will be precompiled. But
yeah, also it probably doesn't help that I'm doing streaming. So after the structural simplify, I have two equations, right? So now the first equation is a algebraic equation, and then the second equation is a differential equation. So like Chris mentioned, we can reduce the system down to a ODE with a internal root finding solver using the ODEE problem. So for the ODE problem, we need to specify the initial condition. So the initial condition, we probably need to specify the capacitor voltage. Do we? Yeah, we need to specify the initial condition for the capacitor voltage. Let's just say it starts from 0, and we want to simulate it from 0 to 10. Yeah, see, so with the ODE problem, there is only one state left. Yeah, and it's solved. Then we can use using plots. Yeah, so as expected, just like the RC circuit, yep, the capacitor voltage is gonna exponentially converging to the voltage source voltage, and then we can also plot the voltage of the resistor also. Yep, and then also see here, the resistor voltage should exponentially decay to 0, right? And then that will be my demo.
yeah. So if you haven't done, Acausal modeling before, right? You basically are just saying like, oh, I know that these voltages are the same. I know that these currents add together. I know this, I know that, I know this, I know that, I know Ohm's law, right? You just list them all out. And then at the very end, you just say, well, get rid of all the redundant equations and solve it for me. And then any of the variables that you want will be there in the solution. So yeah, it is a very nice formalism. So if you've ever used something like Modelica or Simscape, right, that is like those are Acausal modeling systems, and this really shows that that acausal modeling is then just a subset of what Modeling Toolkit can handle, right? So yeah, so let's do a few user questions, and I'll get to some of the last pieces at the end here. Let's see. So there was a workshop yesterday on how to solve differential equations in parallel, distributed in GPU. What is the status of the SciML ecosystem in that regard? We can actually use that tool as part of what we do. You can find an issue on their page about how to use the DiffyQ time steppers with their things, right? So as I mentioned before, right, PDEs are really just generating ODEs, and so what they showed yesterday is how to use the implicit, what was it, the implicit global grids.jl, and the stencil library. I'm forgetting the name of the stencil library, but what those two libraries let you do is they let you define ODEs that use GPU and distributed computations, and so then you can actually just take that and put that inside of your differential equations.jl code. Yeah, so it all composes very nicely. And this is why we're actually working with a lot of the PDE groups for a lot of the examples, right? Because there's no reason for two people to create that. So let me actually kind of pull this up. I forget whether it's implicit global grid or the other one that has. Let's see. I can find it in a sec, or if you ask me, I can find where it's all defined. But there's already examples on the web about how to compose these packages together. So yeah, they do very different things, but you can use them together. And in fact, part of what we want to be doing with the PDE solvers, which I'll show in a second, is that they're actually using all these tools in the ecosystem, right? It basically says, oh, here's a symbolic PDE. Well, let's use this other package to generate the GPU distributed code that then we put inside of this ODE solver. We start tying all these pieces together, and that's how these things work. Let me put this up there to my other screen. Yeah. So could you clarify the difference between compose versus using the subsystems? Yeah, that's because I was using old syntax. You probably should be using compose. That was my bad. Yeah, the compose, they are the same thing. Can you combine Modeling Toolkit ODEs with neural networks, i.e. universal differential equations? Yes. Yes and no. So the issue there is that Modeling Toolkit is still not fully compatible with symbolic arrays. The moment it is fully compatible with symbolic arrays, then you can define these subarrays as parameters, right? The weights of the neural network is just a symbolic array of parameters. And so you can then start to stick all these together, and that's how you can put a neural network inside of Modeling Toolkit. And yes, that is how we're going to make a whole system that can automatically discover equations in a way where you just kind of do things kind of quasi-symbolically, and then make it read your math homework and figure out how to do that for you, integrating neural networks and all that. That is the plans down the line. Yeah, from what I understand, the SciML ecosystem centers around dynamical systems. Steady-state solutions are important in very many disciplines. What is the current support for these? I will show a steady-state system in a second here, so I'll say that'll be answered. Let's see. Are there any other major questions that you're seeing in here? So one, is there any work being done on exporting models as FMUs? Yes. If you watch the talk on JuliaSim, this is this extension to this ecosystem. JuliaSim has a lot of tools that are being added that will allow for FMU imports and exports. Let's see. Any other major questions that you're seeing in here?
Yeah, there is this quite astute question on asking about singularities of DAEs, right?
Mm-hmm.
So basically, right. So you could think about this problem in two different ways, I think. So for instance, if you in the RC circuit that I did before, without any simplification, there is actually there is actually a non-trivial null space in the Jacobian without doing structurally simplify. So structurally simplify can do the alias elimination, and then symbolically eliminate the null space, the non-trivial null space for you. So it wouldn't result in any singularity issues. And then another singularity issue is when if when we index reduce the index 3 Cartesian pendulum, it will actually run into singularity if the pendulum is initialized perfectly horizontally or perfectly vertically. And that requires, so currently our system doesn't quite handle it so well. And then that will require partial state selection and then dynamic state selection. Yeah, so that will be like a future project.
Yeah, basically the structural simplified passes, they'll get better and better over time. They'll handle more of these weird edge cases. Though, at this point, though, most of the edge cases are like, oh, if you initialize everything at exactly this one point, then this is the point that can be weird, right? So like the pendulum straight up or straight horizontal kind of things. But yeah. Yeah, I think that there was one other. So there was one in here that asked, once a function has been registered, can you define rules for symbolic manipulation? Yeah, you can do all sorts of, the whole library is written in Julia, so you can extend it however you wish, right? So here, for example, I'm going into the Symbolic-Utils.jl source. These are the rules that it's doing by default. The rule system is pretty complex, and so literally. We didn't want to go into too much detail on how that's done, but all these rules are defined based off of, they can be dispatching off of traits and all that. But these are just the rules that are handled in Simplify by default. You can instead tell Simplify what rule set you want to work with, and you can just take these rule sets and extend them to add in your rules for your functions. These are just the ones baked in, trig rules and all that, but you can always extend all this however you want. Let's see. Any other questions before we move on to the steady state models and PDEs? Why does the Acausal RC circuit example in the docs have a compile time after the first run? That was a bug in a previous version that was only recently fixed. Recompile should now be casted a lot better. Yeah. All right. I think that's all the major ones that I see that we're going to cover for now. Some of them I'm then going to be answering in a second here. So let me go on with this next portion. Right, so let's go to Modeling Toolkit beyond ODEs, right? So that was all about ordinary differential equations, and most of this talk is about ordinary differential equations because that's where a lot of people do use Modeling Toolkit already. But I want to kind of show that ODEs are really just a subset of this idea of mixing symbolics into numerics, right? And so we handle all these other kind of cases as well. So let's code up some wacky models. So here I want to show what to do with nonlinear systems, right? So nonlinear system is how you'd represent a steady state problem, right? It's just when the left-hand side, when your derivative equals 0. In fact, you could even tell the differential equation solver that you want to solve the nonlinear system version of it instead of the ODE version, and it will automatically do the translation, right? So let's code up one of these. Yeah, when we're doing a nonlinear system, right, we're going to instead of using differential-equations.jl, we will use nonlinear-solve.jl, right? So this is one of the newer libraries in the ecosystem, which is, think about, nonlinear-solve.jl is like differential-equations.jl for nonlinear solvers. So if you go to like the nonlinear system solvers, it has some methods that are built in, but it also has a wrapper for NLSolve. It has a wrapper for MinPack. It has a wrapper for sundials. And so you can use all of the nonlinear solver libraries from this, right? So what Modeling Toolkit will do then is that for nonlinear problems, it builds the output for this library, so that way you can then send it to all possible nonlinear solvers. So what does that look like? You will do using Modeling Toolkit and using nonlinear solve, right? And then at parameters, t. I guess I don't need to parameterize this, but I have it in my notes. So let me build this. Actually, let me build this nonlinear system here. Right, so this is the one that I mentioned before that, you can do these kind of substitutions, right? Let's actually watch this happen. So you do the system and you say that now this is a nonlinear system. with these equations. And one of the things that we do want to handle in the future is we do want to be able to say like, oh, just call it system and we'll figure out what kind of system it is. We're not quite there yet, but we do want to make all of that automatic in the future. In the future, it should be able to automatically know what kind of math problem you have and then automatically choose the solver. But the automatic solver choices are done, of course, but the identification needs some work. But let's take this nonlinear system and let's do structural simplify on it, right? What does structural simplify mean here? Well, it's the same thing. It just means simplify the mathematical model, where the mathematical model is now dispatching on the fact that it's a nonlinear system. And then what you get is you just get one equation with U of 5, right? If you check this, the equations of your simple system are just this one equation, right? This is the only one that's left. Everything else can be reconstructed if you know U of 5. And so here's just a one variable nonlinear system. And we can take this and we can build a nonlinear problem, a simple system, and we need to give it an initial guess, right, for the Newton method. And now it's numerical, and we can call the solver with it. So here I'm going to directly call Newton-Raphson. Oops. Right, and so this is one of these outputs that if you're familiar with differential-equations.jl, these new aspects of the SciML ecosystem, right? Galactic optim, nonlinear solve, linear solve, they all look and feel exactly the same, right? They have problem types, they use the same argument orderings, they have parameters, they're automatic differentiation compatible. All of these things have been extended to all of these wrapper types for these other parts of the ecosystem now. Right, and so one of the things that means is that it also has the indexing defined. So you can say, what's the solution of U of 5, or you can say, what's the solution of U of 1, right? And it didn't have to solve for U of 1. It just knew how to reconstruct it from these equations. So this is how you can do steady state modeling off of this. And you can tell systems, you can promote nonlinear systems to ODE systems. So you can use a nonlinear system as a subsystem inside of a differential algebraic equation, or you can transform these equations that are time dependent to their steady state form. You can do all sorts of transformations back and forth. So that's steady state modeling. Let's go to stochastic differential equations, right? Since we're nearing the end here, I'm going to copy this over. So this looks almost exactly like ODEs, except now instead of just having your equations, you have your noise equations, where if you only give it an array that matches, then it's going to be diagonal noise. If you give it a matrix, it's non-diagonal noise. If that meant nothing, well, then this is just, this is like a differential equation system with randomness added onto it, which is randomness of this form, where, this is, you have basically, plus rand times rand n, right? You can think about it as this kind of symbolic system where there's randomness added to each term now. And so you can generate this symbolically, right? And now you have the symbolic SDE system. And just like with the ODE system, you build these parameter maps to tell it how to build initial conditions and parameters. You solve it, and then you plot it, and you can plot it using the variable, right? We have a lot of plans for what to do on SDE systems because there's a lot of different specializations you can do, and generating fast code for this. Not all of them are completed yet, but you can see. But at least you can build things, and you can. I think you can even do some structural simplification, and then do solving and plotting. Yeah, let's see. Oh, I probably shouldn't have let it do the automatic algorithm choice. I'm not sure which algorithm it chose for that. But while that's going, let me go to, so the next kind of system, right, is an optimization system, right? So there's a question earlier about JMP, right? And JMP in its ecosystem has really focused on, linear solvers and convex solvers and all this, right? But the nonlinear portion hasn't really been its focus. And so there's always been these libraries like Optim and Black Box Optim that people have been using in the ecosystem, right? What we've done with galactic optim.jl is we've wrapped all of these, we've wrapped local and global optimization packages. So it's beyond global, it's galactic. And so all these packages that you would want to use, like NLOpt, black box optim, but also all of the methods made for jump, right? So IPOpt, right? Or IPOpt. That one is accessible through the MOI integration, the MathOpt interface. And so this gives you a way of being able to call any of these possible optimizers from an interface that looks a lot like differential-equations.jl, right? Where you have an optimization problem and you solve and it dispatches across. And so the reason why we did this, of course, is because now this gives a form such that Modeling Toolkit can build this optimization problem for you from symbolic forms. Right, so what does that look like? So here is our stochastic Lorentz equation, doing tons and tons of steps to, tons and tons of steps to be able to really accurately solve this kind of wacky system. Now let's look at the optimization problem system, right? So in this case, now we do using Modeling Toolkit, Galactic Optim, and Optim, right? Because we're going to use Galactic Optim as our solver interface, but we're going to grab the solver from Optim. The variables that I want to define my optimization problem on is x and y. And then I want to have parameters A and B, right? Just like the rest of the SciML ecosystem, these are optimization problems with parameters. So that way, at least in the near future, I'll be able to differentiate with respect to the parameters. So let's define an optimization problem, right? So this is all built for nonlinear optimization right now. Though I do have a student who's working on building some nice convex modeling tools based off of this whole ecosystem. So here is the loss function that we want to minimize. And so an optimization system is just defined by what is that loss function, what are the variables, and what are the parameters, right? It just feels very similar to the rest of what we did before. So now you say, well, what is my initial guess for my local optimizer? You can just kind of slap in some initial guesses. Some optimizers might not use the initial guess, and that's okay. Then you give it to your parameter values. And now we build a problem where this time now it's an optimization problem, right? It's a different type, but it's the same idea here. The argument orderings and all that are the same. And like what Yingbo showed, right? We can generate Jacobians and gradients and Hessians. So let's actually tell it to generate the analytical solution to those gradients and Hessians. So that way we can use a Newton solver using our Hessian functions. Oops.
There's a typo in the comment.
Yep. Right, and then it tells you the solution here. I think the symbolic indexing should be good here. We haven't set it up on the optimization function. So yeah, the optimization one, it definitely needs a little bit of work. There's a way, for example, to be able to define constraints and such, but it doesn't necessarily pass all the constraints onto onto all the solvers yet, which is why the documentation currently says optimization is a little bit of a work in progress. But you can see how this is going to be a very nice system for optimization. One of the things that should be coming soon, right? As I mentioned, you can put nonlinear systems inside of ODE systems and it'll upconvert and such, right? The way that we're doing control systems is to say that you can have an optimization problem that has a subsystem that's an ODE, and it will know to solve the ODE to be able to define its loss function and be able to use the solution of the ODE, its time series. So this is still a little bit of a work in progress, but you can see that there's already a lot of elements there that can be useful. Like, if you write down this optimization problem, you can have it generate Hessians and such for you. Now let's go to another example. I'm going to be really quick here because we only got a few minutes. So here's an example where I'm going to grab one of these DSLs that works with Modeling Toolkit. Right, so I'm going to grab this from Catalyst. And just want to also show that these all have LaTeXification on them. So if you do want to like put this in a paper or something, you can ask it, what is the LaTeX for my current model? This is the chemical reaction model in LaTeX. You can do this for ODE systems and such as well. But the way that you can simulate here is you can say, well, just turn this into an ODE system, and it knows how to translate this reaction system that we had into an ODE system that is then going to be simulatable by our our methods for ODEs, right? So you can define parameters and initial conditions. And now here I'm just the documentation here is showing a trick where you can say, well, if I know what the ordering of my species are, right, I can use this to be able to create those pairs that I did before. And so this is just like a nice little trick if you do know the ordering, where something like this DSL doesn't change the ordering, right? So you define an ODE problem, and then you can solve this ODE problem. So it's just like another way to be able to read in and get ODEs. And this is how things like the SBML reader works and all that. So there's a lot of file readers which are using these kinds of reaction tools to be able to generate ODE systems. And so yes, all of the optimizations, parallelism, etc., extends to Catalyst and every library that uses Modeling Toolkit. And so there seems to be a lot of videos going up on YouTube where it's like, oh, here's orbital dynamics 10 times faster than the libraries before. Here's powersystems.jl, 10 times faster than those before. Because everyone who's using Modeling Toolkit gets to claim the speed up, right? So there's like a nice gold rush there, which is kind of fun. There's also all these other problem types that if you look at differential-equations.jl, it says there's you can handle these jump systems, you can handle these discrete systems, and do Gillespie methods, and of course there's all these symbolic ways to be able to represent those as well. And so you can here's a purely this is a differential equation defined on integers, which has discrete jumps at continuous times, and you can run this and solve this as well. So as the very last example here that I want to make sure we do is this solving partial differential equations by neural networks, right? So there are many different ways or many different libraries that are being developed for handling partial differential equations from this one symbolic form. And as I mentioned, this is using pieces like, we're interfacing with groups like GridApp. We're interfacing with groups like, well, the diffq operators. This is with the pins. We want to interface with the group that did the workshop yesterday. We're going to be working with a lot of the Julia ecosystem. So that way you can write your PDE in one way, but use everyone else's libraries just by switching one line of code, right? And the line of code is discretize. The idea is that from a symbolic PDE system, all of the different ways of solving a PDE are just ways of changing that PDE into some numerical problem, either a optimization problem, or a nonlinear system, or a ODE system, right? All these other types of solvers, right? PDE methods are just methods for translating symbolic PDEs to those. And so it just is another transformation in the Modeling Toolkit world. Just because it takes a while to run, I don't think I'll run the pin right now. But what you really do is you just you define your parameters, you define your variables. Here I'm making it so that way this is saying that it's an open system. So by default, U is just a function where you need to put in what it's going to have here. The reason why I'm using that open form is because when I'm defining my boundary conditions, I want to say, well, when x is equal to 0, make it be this. When x is equal to 1, make it be this, right? But the syntax and the flow in the symbolics is all the same as what we showed before. So this is now just defining a system with more than one independent variable. And so this then gives you a PDE system where we then say, well, the way I'm going to solve this is I'm going to build an optimization problem where the optimization is defined by a neural network. And when you solve the optimization problem, the neural network will become the solution to a PDE. This is the physics-informed neural network approach, and you can see Zoe's talk at JuliaCon for more information on how it works. But yeah, so now we just have an optimization problem after this discretization, and so we just send it to an optimizer. And after it runs for a little bit, you plot the solution, and you have the solution to your PDE. Right? So this is this PDE system that is all kind of growing out of Modeling Toolkit, where all of these different ways of handling PDEs can be done under one single interface. Physics-informed neural networks and finite difference methods and finite element methods, finite volume methods and spectral methods can all be abstracted for you. And the only line of code that would really need to change is how do you tell it to discretize. So this is something that's really cool. It's still kind of in pieces, and we're looking to work with a lot of other developers to do this and get it up and running fast. But it is already growing to something that's usable. And for example, we're just about to merge support for things like integral differential equations and fractional derivatives inside of the PDE solver, the physics-informed one. So it is a very general form that can be optimized in very nice ways. So yeah, that was all that we had for you. Let's see if there was any remaining questions at the end here. Yingbo, did you take a look through the questions to see if there's any that you wanted?
No, nothing in particular. So there is a question asking how structural simplifier works, but that takes a really long time to explain. It's not
structural simplify is a very big algorithm, and for different system types, it means something different too, right? Because it's also multiple dispatching. So if you want to know more, you can come talk with us. And in fact, if you're interested in this kind of work with Julia Computing, I am recruiting a lot of interns, and I'm recruiting interns, and I'm recruiting for full-time positions as well to be able to build out Julia Sim. Which, watch the Julia Sim video, it adds a lot to this ecosystem. It adds a lot of cloud compute, and it adds a lot of machine learning integration to it, and it really ties into this whole system that we've been building here. So yeah, if you want to learn more though, we can chat. That'll be more than a 3-hour chat though. Let's see. Yeah, I think that since we're at time, any of these other questions, if you can send emails, message us in Slack, message in the Discord, right? If you don't know about the Slack, right, you can go to the Julia Lang Slack to be able to get on here. What you would do is you go to julialang.org. You go to julialang.org. You go to the community tab, and then you look at how. Where is it? Yeah, so you go here for the official Julia Slack, and this will give you an invite. You can use this to be able to ask for an invite. They missed this. Yeah, so if you click here to join the Julia Lang Slack, if you aren't already in it, then it'll give you an invite. You can join these channels, DiffyQ-Bridged, SciML SysBio, which is all about the systems biology group that's been building around Modeling Toolkit, SciML Bridge, which is about these physics-informed neural networks and these types of tools. And also we have this symbolic manipulation, which is all about some of these symbolic tools. So there's a lot of different channels where people are talking, and if you have a lot more questions, we can field those for days. So anything else you want to add, Yingbo?
No, yeah.
So yeah, thank you very much for coming to our workshop. I hope that it was very informative. We definitely had a lot to go through, and that's still only a very small sliver of what Modeling Toolkit really does. So the last thing I'll mention is, try and support us however you can, or if you're interested in some of these positions, come talk to me. If you're interested in contributing, come talk to me. If you just find this really cool, just send a message that says it's really cool. Or, another way to contribute is you just write tweets or blog posts that just say, I found this really cool. So yeah, thank you very much.
Thank you. Bye.